Hi everyone, good morning. So welcome to today's GCSE chemistry session. Thank you all for joining me on a Sunday morning. So today we will be looking at crude oil and fuels. So I think the majority of you were here yesterday, but for those of you that weren't, welcome. My name is Roshni and I will be doing today's class. So I'm currently a doctor working in London and I've been working for 3 years now, and I studied at King's and at Imperial. I've also been a science tutor for many years now, and this is just a screenshot of my A-level results. So I studied biology, chemistry and maths, and as you guys can see, I was very lucky and I managed to score nearly full marks in all my exam papers. And I haven't put this in to show off or to brag, but rather to show you guys that this is very much attainable, and it's something that you can achieve if you are just given the right direction and some guidance. So that is what I hope to do. If you guys have already heard me say this, sorry. Okay, so what are we going to be covering today? So we'll be doing a few very interesting topics. So we're looking at crude oil and fuels. And within that, we'll be looking at hydrocarbons, fractional distillation of oil, and burning hydrocarbon fuels. And then later on, we'll be looking at cracking as well. And then we will also be looking at organic reactions. So we'll be talking about alkanes, which come up in the first topic, and comparing them to alkenes. And then we will also be looking at alcohols too. So this content that we have, that we will be delivering today is relevant to all major exam boards in the UK. If you are doing double science or triple science, then there is some extra stuff that you need to know, but I've taught students from all exam boards, so I will point you to extra things that you might need to know and signpost you to this. Okay, so what is today going to look like? So we're going to start off by looking at hydrocarbons, and you will get a break every 45 or 50 minutes or so for about 10 to 15 minutes. And later on, we'll be looking at fractional distillation, and we will go for a lunch break from 12 to 1. And in the afternoon, we'll be looking at hydrocarbon fuels, and finally ending with alcohols. And then we will be doing some exam practice at the end, but we'll also be doing exam questions throughout the day as well. Okay guys, so during the session today, if you have any questions or you don't understand what's going on, you want some clarification, please do just ask. So my colleague Ask Ace is also sitting in on the session, and they are there just to answer your questions. So please do ask them if you are a bit lost. We will be doing lots of Kahoot quizzes today. I know you guys enjoy doing these. So whenever you see this logo coming up, there's a quiz coming up. So do make sure you pay attention. And finally, we have got top tips. So whenever you see this light bulb sign, essentially this is a definition or it's a concept that you should be very familiar with, and it's one that you want to take home from the class. Okay, guys, so we're just going to get straight into it. So can anyone tell me, do you guys know what this is in this picture? Just put your answers in the chat. Okay, so this looks like a very murky black thick substance, but this is actually very useful, and we use this for many different things in the industry. So this is known as crude oil, okay, and it looks like this gloopy substance, but actually it can be converted into lots of different things, and this is basically what the focus of today's session is on. Okay. So crude oil. So there are lots of different things that we can do with crude oil. Does anybody know what these are? So great, so we can actually use crude oil for lots of different things. One of the main things that we can use it for is as a fuel. Okay, so it can be used as a fuel in aeroplanes, even in cars as well. So all of the cars that we use, they are running on fuel, and that fuel comes from crude oil. Okay, we also use crude oil for making plastics, so water bottles and lots of different objects that have plastic. All of these are made from crude oil. So you can appreciate that this is actually a really useful substance. So you might be thinking, why do we have to learn about crude oil? But actually, we use it in our day-to-day life very frequently. So it's really important that we have a good way of extracting that oil and converting it into ways that can be beneficial for us. Okay, so crude oil just looks like that black substance, but what is it actually made from? So as I said, so some of 21st century's most important chemicals, they come from the organic carbon compounds found in crude oil. And these chemicals are really important and they play a major part in our lives. And basically, the reason that crude oil works so well and why we can use it for so many different things is basically because it's made of carbon compounds. And carbon is an amazing element that can actually be converted into lots of different things. And we will see in its chemical structure. So the carbon atoms, they can be bound to each other to form chains and rings. That form these skeletons, and I will talk about this. So the main take-home message is that basically crude oil, so that thick substance that we saw in the beginning, the main thing that is made from is carbon, okay? So it's really important that you have a good understanding of the element carbon because this forms the basis of crude oil. Okay, so just so that we are really clear about carbon, so as I'm sure you're aware, this is a periodic table, and at the top we have got our groups, so this is group 1, etc., and then we have got our periods going across. Now, we're not talking about the whole periodic table. I just want to highlight the main element which we are talking about today, and that is carbon. Okay, so you will know that carbon is on the right-hand side of the periodic table, so it is a non-metal. Okay, and the properties of carbon are very unique, and this is why we can use it from the crude oil. So we are mainly talking about carbon today, and we will also be talking about hydrogen. Okay, both of these are in crude oil. And if you guys go on to do A-level chemistry, carbon is a huge chapter and it comes under organic chemistry. So it's really important that we get our basics clear. Okay, so this is what we're talking about. We're talking about organic chemistry, which basically just means talking about carbon. So in the periodic table, you will see that carbon has got a 12 at the top and a 6 at the bottom. Okay, so just to make sure that you guys are awake, guys, what is at the top? If you can just fill in the poll, what is number 12? Okay, guys, so some very split answers. So half of you have said mass number and half of you have said atomic number. So guys, the number at the top, the bigger number, okay, that is my mass number. Okay, so at the top here, this is my mass number. And at the bottom is my atomic number, okay, because this number is smaller. In some periodic tables, they might write it the other way around, but you need to look at what the number is. The mass number is the total number of protons and neutrons, okay, and my atomic number is the number of protons, okay, and this is very basic chemistry, the number of protons is equal to the number of electrons. So just to make this very clear, I'm just going to draw out my diagram. So, if we have to draw out what it looks like, we've got a nucleus in the middle. And then remember that the electrons are arranged in shells, okay? So my first shell, so I know that carbon has got, if it's got 6 protons, it must have 6 electrons. The first shell will hold a maximum of 2 electrons, okay? And the second shell will therefore hold 4 electrons because 6 minus 2 is 4, so it will have 4. Okay, so all of these that I've just drawn, those are electrons, and remember that in the center over here are my protons and neutrons. So those are the protons and neutrons sitting in the middle, and on the surrounding it, I've got my electrons, okay? So this is the basic structure of carbon, and the key take-home messages is that carbon has got 4 electrons in its outer shell, and this will very much dictate how it will bond and how it will react. Okay, so you can see that a nice diagram here. This is our mass number and our atomic number here. Great, so as I've said, so carbon is in group 4 of the periodic table, and we've got 4 electrons in our outer shell. Okay, 1, 2, 3, 4. So what that means is because carbon has got 4 electrons, that means that it can form 4 covalent bonds to other atoms. So you'll remember that a covalent bond is a shared pair of electrons. And these bonds that it can form, so they can be single, they can be double, and sometimes they can be triple. So basically what we mean by that is that if this is a carbon, okay, so sometimes it can form single bonds like this. Sometimes it can form a double bond, shown by 2 lines, and sometimes it can form a triple bond, okay? But what I want you guys to remember is that carbon can only form a maximum of 4. So if, for example, let's say carbon is bound to hydrogen like this, okay, this is correct because carbon has got 1, 2, 3, 4. Okay, if you start drawing a carbon that is attached to 5 hydrogens like this, okay, something has gone wrong because carbon has only got 4 electrons. So there is no way that this exists. This is completely wrong. Okay, and this will really help you to identify molecules and to name them. Okay, so just remember that we can only form 4 bonds. Okay, so carbon atoms can bond to other carbons to form long chains. Great, so we've talked about carbon, but you will remember that basically in the beginning we said that we've got something called crude oil, and basically it's made up of 2 things, hydrogen and carbon. Okay, and because we want to extract this crude oil, it's very useful for us to name this, and we basically call both of these things. So you will see here that what do both of these molecules have in common? Just have a think about it. Great. So the main thing is that there is a single, these are single bonds, okay, and these ones are, this is a double bond here, but you will see that both of these compounds, they're only made up of carbon and hydrogen. Similarly here, we've only got carbon and hydrogen. And whenever you guys see these molecules that have just got carbon and hydrogen, we call them, understandably, we call it a hydrocarbon, okay? So hydro coming from hydrogen, okay, and carbon is obviously just carbon, okay, and this is like a really common 1-mark question, like what is a hydrocarbon? And a hydrocarbon is a compound containing carbon and hydrogen only. Okay, you must say the word only, because if you start adding something else, like let's say you add in bromine, or you add in anything random like sodium, okay, this is no longer a hydrocarbon. It can only have carbon and hydrogen only. So that is just an introduction. Today we will be looking at lots of different hydrocarbons. Now there are loads of different hydrocarbons. There are lots of different molecules that carbon can make because it's very versatile. One of the main things that carbon can form, okay, is something known as an alkane. Okay, if you've not heard of this word before, don't worry, we'll go through it. So basically, a very common group of hydrocarbons are known as alkanes. And you know something is an alkane is basically because the name ends in ane. Okay, and that's how you know. And we'll see different compounds later. So it's really important that you remember that there is an A here. Now, when we name these alkanes, so the first part of the name of each alkane will basically tell you how many carbon atoms are in its molecule. Okay, so the first one, so if we have got one carbon atom in the molecule, if we've got one carbon, it basically starts off with meth, okay, and then it ends. If we have got two carbon atoms, we name it as eth, and we just get rid of the M. If we have got three carbons, and I'll show you guys a way to remember this, so don't worry, we call it prop. And if we have got four carbons, we call it bute. Okay, so it's meth, eth, prop, and bute. Okay, and as you guys will see here, so the start of the name, which is known as the prefix, okay, this is basically telling us how many carbon atoms there are. So if it's meth, it's 1. If it's eth, it must be 2, and prop is 3, and bute is 4. Okay, so how do we draw these compounds out? Okay, so because these are all alkanes, essentially all of the alkanes, as we've said, they end in ane. So this would be methane, and methane, we said, meth means one carbon, and ane is telling us that it is an alkane. So I know I'm going to draw one carbon, okay, and we are looking at hydrocarbons. So I know that these can only have hydrogen and carbon only. So this is what my structure of methane will look like. Remember, carbon can only form 4 hydrogen bonds, so I cannot add on any extra other one. And this is methane, okay? This is a very simple molecule, and crude oil is got lots of methane inside of it. Okay, so if I want you guys to just draw on your piece of paper, if you can draw ethane with me. So remember, we said that eth means that we've got 2 carbons, and ane is telling us that it is an alkane. So I'm going to draw my 2 carbons here. And now I know that carbon can only form 4 bonds, right? So this carbon has already got 1 bond here. So I can draw 1 more. Okay, and this carbon has now got 1, 2, 3, 4. And again, I can draw 3 hydrogens here. So each carbon is bonded to 4 other elements. And this is my structure of ethane. And you can see that very clearly over here. And just so that you guys know the naming, so as we've said, so eth means that there are 2 carbon atoms in the molecule, and ane is telling us that it is an alkane. Okay, so finally we have got propane. So prop tells us that there are 3 carbons. Okay, and ane is telling us that it is our alkane. So I'm going to start off with my 3 carbons. I know these are all joined together. And then I'm going to fill in my hydrogens because these are hydrocarbons. So I can put 1 here, 1 here, and 1 here, and that's it. Okay, I've now got 4 bonds. I can put 1 here and 1 here. That will give me 4. And I can put 1 here. Okay, so this is my basic structure of propane. Okay, so I'm sure you guys are getting the hang of it now. So finally, we've got bute. So bute has got 4 carbons. Okay, and again, it's an alkane. So I've got 1, 2, 3, and 4. Okay, and then I'll just fill in my hydrogens now. So you'll see that each carbon has got a max of 4 other things that it is attached to. Okay, so how do we remember this? So you will basically, we've talked about there are four. So we've said methane, ethane, propane, and butane, but actually there are loads. Sometimes this carbon chain can extend to like 10 or 20 carbons. But for GCSE, you only need to know the first four. Okay, so how do we remember them? So we've got alkanes and we've got methane, ethane, propane, and butane. So the mnemonic that I used to use was monkeys eat peanut butter. Okay, so this will help you to just remember in the beginning. Once you keep practicing, then you should be able to remember the names, but this will help. So we've got monkeys for methane, eat for ethane, peanut for propane, and butter for butane. Okay, guys, does anyone have any questions on that so far, or are you guys okay? Okay, great. So we're continuing to talk about these molecules which are known as alkanes. And what you will see in common with all of these alkanes is that they are basically saturated. And what we mean by saturated, you may have heard of the word saturated as sort of like, you know, if you say your brain is saturated, like you've had enough, and basically there's no more space. So saturated means that you cannot add anything else on. Okay, and we describe alkanes as saturated hydrocarbons. And what that means is that all of the carbon-carbon bonds, i.e. this bond over here, they are single covalent bonds, okay? So we do not draw double bonds. This is not an alkane. This is another molecule, and we'll talk about this. So these are all single bonds. And this means that they contain as many hydrogen atoms as possible. So what that means is because this bond here is full, we can't just add on another hydrogen and put one here, or add one on here. There is already 1, 2, 3, 4. Okay, this carbon is saturated. It's got enough hydrogens, and it doesn't want any more. Okay, and the situation changes when there is a double bond, and we'll talk about that later. So it's important to just realize that alkanes are saturated and they have only got single carbon-carbon bonds, and no more hydrogen atoms can be attached. Okay, so we covered the four main ones. So remember, we said that we've got methane, and then we've got ethane, which has got 2 carbons, and propane and butane. But as I said, actually the chain can be very long, particularly in that crude oil, in that thick substance we saw in the beginning. They can have chains that are actually like got hundreds of carbons. So their chain can literally be massive like this. Okay, now obviously we can't sit there and count and see how many carbons are there, how many hydrogens are in this massive chain. So we can come up with a formula. And what that formula is it's CnH2n plus 2, okay? And we basically describe this as a general formula. So the general formula for alkane molecules can be written, and you might be wondering what N is. So N is equal to the number of carbon atoms. Okay, so for every N carbon atoms, there are 2N plus 2 hydrogen atoms. So let's say, for example, let's say we take our first example. So we said that propane, okay, has got 3 carbons, right? So if I put in a 3 here, I will have C3, and I will have H, 2N plus 2, and 3 times by 2 is 6, and 6 plus 2 is 8, right? So it will give me C3H8. And that is correct, because if I draw out my propane, okay, I put a HH. Okay, if you guys just count these, okay, you will see that there is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this works. We know that this is C3H8. And this general formula works for literally for any number of carbon that you put in. So you can even put in like C100, okay, and then it would be 100 times 2 is 200 plus 2 would be H202. Okay, so you can pretty much do this for any compound, and sometimes they can give you like really longer ones in the exam. So you obviously can't sit there and draw out, 100 carbons. You have to use the formula. And yeah, so for example, if an alkane molecule has got 12 carbon atoms, so then I would do C12, and then 12 times by 2 is 24, and I add on a 2, which will give me 26. So I know that the formula is C12H26. And this is really helpful for us because when we try and separate out that crude oil, all of the chains have got different lengths, and we can't obviously sit there and count and see how many are there. So it's very nice that we've got this formula. Okay, guys, so I'm just going to test you guys now. So I've put the formula here. So what do you guys think is the formula for propane? Okay, and I will just help you guys out so you can draw out propane. Remember, we are on monkeys eat peanut, so propane is 3. Okay, fantastic, guys, and pretty much everyone has said C3H8. Okay, and then what about butane? Great, so butane is C4H10. Okay, so remember but is butter, which has got 4 carbons, and we've got 1, 2, 3, 4 here. And you can easily plug this into the formula and you'll get C4H10. Okay, great. So let's just do a quick exam question on what we have covered now. So the simplest hydrocarbon is methane. Its structure can be represented as this. So draw the structure of ethane. Okay, guys, so hopefully you've had a chance to do that. So remember, ethane is, they're telling you it's C2H6, okay? So this is a nice and easy 1 marker. I've got 2 carbons, and then all I need to do is fill in my hydrogens. Okay, they've already shown you what methane looks like. So this would be ethane. I can see here I've got 1, 2, 3, 4, 5, 6, and I've got 2 carbons. Okay, great. So just a quick recap. So identify the following molecules. So guys, very quickly, what do you think this one is? Fantastic, this is butane, well done. So that is butter, there are 4 carbons. Okay, and just this one. Okay, amazing. Well done, guys. So this is propane. Someone has said methane. So methane has got 1 carbon, and methane looks like this. Okay, so this one is propane because we've got 1, 2, 3 carbons. Okay, fantastic, guys. So we've got the basics very clear, and this is very important because when we talk about fractional distillation, etc., it can get a little bit more complicated. So we've got our 4 hydrocarbons that we're very familiar with now. So the properties, i.e. when we talk about properties, all that means is the way that they react. So like their chemical, how they react in chemical reactions. These actually differ quite a lot. There is a great variety in how methane will react versus how butane will react. So some of our hydrocarbons, they're really small. Okay, they look just like this, but some of them are actually much longer. The thing is that the short chain ones, they tend to be the most useful. And this is why in crude oil, we've actually got ones that are like really, really long, and we try and break them up to make them tiny, because these ones, they are much more useful, especially when we use them in petrol. Okay, so as we said, the properties of the hydrocarbon will vary very much depending on their chain length. Okay, so this one we know here, this is methane. This is the simplest hydrocarbon, it's CH4. At the bottom, I've got here a very long complex molecule. Okay, this is got 10 carbons, so this must be C10 H22. Now, obviously, you guys, I'm sure you can imagine that if I was to react this with something and I was to react this with something, it's a huge difference, because this molecule is very long and this one is very short. Okay, so there are four main things that we like to compare between short chain. We call this a chain. So this is a short chain molecule, and this is a long chain. Okay, chain because this is like appearance of a chain. So the properties very much will vary, and we will talk about why and what happens. Okay, so the first one is boiling point. Okay, so what do you guys think will happen to the boiling point as we increase the chain length of the molecule? Okay, so if I'm going from a molecule, if I have to boil this one or I have to boil this one, do you think that the boiling point will increase as the chain length goes up, or it will decrease? Great, so a lot of you have said increase. So let's just talk about this. So remember, the point at which something boils is the point at which something boils is when it turns from a liquid to a gas. If you want to boil something, you basically have to break up all these bonds, okay? Now here, I've only got 4 bonds, so it won't take too much energy or too much, the temperature doesn't need to be too high. But if I have to break up every single bond here, to try and break up this molecule from a liquid to a gas, it's going to take a lot of effort, isn't it? And therefore, the boiling point will increase. You need a higher temperature. Here you might only need like 4 degrees, and here you might need 40, okay? So as the chain length is increasing, the boiling point is also increasing, okay? So increase in chain length, we will have an increase in boiling point. And I don't want you guys to just blindly memorize this, okay? It's important to understand, and this is very logical, because you're trying to break way more bonds here, so it's going to be harder, and we will have to increase the temperature. Okay, so we have something called viscosity, okay, and what viscosity basically means is it's how thick a fluid is, basically. So how thick any substance is. You may not have heard of this word before, but a very simple way of looking at it is, here I've got water and here I've got honey. Okay, so you can see in the diagram, like, which one is thicker? Is it water or honey? Obviously it's honey, right? Honey is much more thicker. So we say that honey is more viscous and water is less viscous. Okay, and that's all it means. It means how it flows, or how thick the fluid is. Okay, so what do you guys think will happen to the viscosity of these hydrocarbons as the chain length increases? So do you think that they will become more viscous or less viscous? What do you guys think? Okay, so majority have gone with increase, but a couple of you have said decrease. So do you guys remember in the beginning, I showed you crude oil and it was that massive, thick, gloopy substance, okay? So what tends to happen is this one, there's just 4 bonds here, right? So it's not gonna be very thick. It will be quite runny because it's very small. There's just a few bonds. Now we've got this massive compound, okay? And because there are more bonds, essentially it's much more thicker. Okay, and it's more thicker and therefore the viscosity will increase. So you can just, this is sort of like water and this is like honey here as we increase the chain length. Okay, so the shorter chain length so here, this is a short chain length, i.e. this one. So this is very runny. Okay, so our viscosity is therefore low. It's just like water. And then as my chain length goes up, okay, the viscosity is high and it becomes thick. So this is a long chain length. And crude oil is that thick, gloopy substance. So a lot of crude oil is basically made of these chains that are so long, and that's why they're very thick. Okay, well done, guys. So flammability. So flammability is basically, you can think of it as a flame. It's how easily something burns, okay, and how easily we can light it up. So what do you think will happen to the flammability as we increase the chain length? Do you think it will go up or it will go down? Okay, guys, so we're literally split. So we've got mixed answers here. So this one is a bit trickier. Now, basically, flammability is telling us how easily something burns. If I've got one little molecule, okay, it's gonna be quite easy for me to set this on fire because it's very small. If I've got this really long chain, okay, it will take a bit of time for it to burn, won't it? And I'll have to put in much more stronger flames and heat it up more. So as we go down, as the chain length increases, the flammability will actually decrease. So it's the other way around. So these ones are less flammable. Longer chains are less flammable because they are much longer. Okay, so it's harder to set this on fire. If we've just got a small little chain like this, they are more flammable. Okay, so shorter chains have got a higher flammability. So just think about the definition if you find this confusing. Flammability means how easily it burns. So this is not easy and this is easy. So that's why the flammability is going the opposite way. Okay, great. And there's one last one, which is volatility. And basically what volatility means is it's the tendency to turn to a gas. Okay, so these words, they might be unfamiliar to you, but we will keep using them. And if basically what it means is how easily do we go from a liquid to a gas? So do you think that the volatility will increase as the chain length increases, or will it decrease? Okay, amazing, guys. Well done. So it will, the volatility will decrease as the chain length increases. And this is purely because it's going to be much harder to turn this from a liquid to a gas, okay? Because what we need to do is we need to boil it, basically. We need to heat this up. And it's very easy to just heat this up, okay? It's so small, it will just turn into a gas quickly. But this one is going to take a while. And therefore, the ability for it to turn into a gas is much lower. So here we've got a low volatility. This will just stay as a liquid, okay? So this, you can imagine this is like crude oil. Crude oil doesn't just turn into a gas straight away. It's very thick and it's a very long chain. However, if we've just got a very simple compound as methane, this is one carbon, this will easily just turn into a gas, okay? Because it's a much shorter chain. So guys, just to recap that, so you're all very clear. So this is a short chain here, and here we've got a long chain. There are 4 things that we are comparing. So as our chain length is increasing, okay, the boiling point is going up. So we will have an increase in the boiling point because obviously we need more energy, okay, and we need higher temperatures. The volatility, which is our ability to turn into a gas, that is going to decrease, okay, we've just said that. So the volatility decreases as the chain length increases. So these two are basically the opposite of each other. And then the viscosity, which is how easily it flows, this increases because it becomes more thick. And then the flammability, which is how easily it burns, so that will decrease. Okay, so the flammability will decrease as the chain length increases. Okay, and I know these might be a lot of new words, but it's just good to try and understand why this is happening. So just picture in your mind that short chain that we have, and then the long chain. So you don't need to try and memorize like which one is up and which one is down. Rather, you want to think about it and understand, you know, why would it increase and why would it decrease? Okay, great, guys. So we'll just pause there and do a quick quiz before we go. So I'll just pause this and we will get our Kahoot up. Okay, fantastic, guys. So this is butane. It's not butene. This is an alkene, and we will talk about this. Oh, okay, so this one is CH4. I think they've just put a lowercase here. So I think any of these 3 would be correct. Yeah, that's CH4. Fantastic. So crude oil is a mixture of hydrocarbons. Okay, so they contain hydrogen and carbon only. Okay, so we'll talk about this next. That's right. So it actually took millions of years, and we will talk about how it was made. So well done. Okay, great. So it's CnH2n plus 2, guys. So those of you that said this is wrong, this is for alkenes. We'll talk about this. And this one, there's no N here. So this is a bit of a trick, but there needs to be an N here. Otherwise you'll only have one carbon all the time. So great. Okay, guys, so this image here is propane. Remember, it's monkeys eat peanut butter. So propane will have 3 carbons. So it must be this one, okay? This is methane, this is ethane, and this one is butane. There are 4 carbons, okay? So well done. Okay, and last question. I've given this one away. Fantastic. Propane has got 3 carbons. Okay, monkeys eat peanuts, so it's 3 carbons. Fantastic, guys. Well done. So we will just go for a quick break. So if you guys come back at 11 o'clock, and we will continue there. So grab yourselves a drink and see you at 11. Hi everyone, welcome back. So I hope you enjoyed your break. We're just going to continue from where we left off. Okay, so we talked about hydrocarbons and we talked about alkanes. We're going to go back to talking about crude oil and how we can actually separate this mixture. So you can see that it's a very thick, dark substance, but crude oil is used as a fuel, as we've said, and to get it into that fuel, there is a process that needs to take place. Okay, and we're going to talk about what this process is and how it works. So as we said, we need this crude oil because it's used in many things, and we wouldn't even be able to travel if we didn't have crude oil because it's a major source of fuel. So these organic compounds are those which contain carbon, like crude oil. We use them as fuels to run our cars, for our heating, and we also use it for electricity. So you might be thinking, why do I need to learn about crude oil? But actually, it's really important and relevant. So fuels are important because they keep you warm and on the move. And therefore, with things like oil prices, sometimes they can go up and they can go down, and this is a huge industry. So countries that produce crude oil, they can affect the whole world economy by changing their prices. Okay, so we're going to talk now largely about crude oil and how we can extract it. So we can describe crude oil as a finite resource. Okay, finite meaning that it finishes and it's something that gets used up. Okay, we don't have it forever, it will run out. Okay, and this is the opposite of infinite, which means it will always be there. Okay, so it's a finite resource, and actually, where does this substance come from? Well, it's actually formed from rocks that are deep inside the earth. So I'll show you guys the diagram, but basically this cropped up in the quiz, but over millions of years, essentially what happens is that the animals and plants that sort of died and decayed, they became buried in the soil and in the mud. And over years and years, what happened was rocks were built on top, and that rock caused a lot of high temperatures and high pressures to make this oil. So basically we can see that over here. So this was our ocean around 300 to 400 million years ago, and we had all of these sea animals and fish in the ocean. And then basically what happened was when they died, some of their remains just sort of sunk at the bottom. So they died, and then these plant remains went to the bottom. And basically what happened is over millions of years, okay, this didn't just happen overnight, but there was sand was deposited, and then the sand and silt turned into rocks, and those rocks, they caused a lot of pressure to the plants and animals, and it eventually it created this oil and this gas. Okay, and that's where the crude oil came from. So it basically comes from deep underneath the ocean. So you can imagine there's a lot of processes to try and get that oil from down here and to convert it into a fuel so that you can use it in your car. Okay, so this is a very long process, and this is a finite resource. Okay, because eventually we won't have any plant and animal remains, and it will take a very long time to get this back. So we have to be very careful with how we are using it. Okay, so as I said, the crude oil is a very dark and smelly liquid, as you can see it over here, and it's basically a mixture of many different compounds. Okay, so it hasn't just got, loads of propane inside, it's got millions of different carbons of chain lengths. And a mixture, as you should know, is one that contains two or more elements or compounds that are not chemically combined together, so i.e. they are a mix. So there may be some propane, then there'll be like a really massive long chain, and they will all just be grouped together inside the oil. And as I said, nearly all of the compounds in crude oil, they are compounds containing only hydrogen and carbon. So sometimes crude oil can have some impurities, and it can have like some other metals very rarely, but usually crude oil is just hydrogen and carbon, and that's all that there is inside. And we already know that we call these hydrocarbons. Okay, so guys, how do we get from this dark liquid to a fuel that we can use in our cars? So the process that happens is called fractional distillation. Okay, so that is how we separate crude oil, because we know that crude oil is a mixture of different hydrocarbons and we're trying to break those up. So we separate it via fractional distillation. And the reason that we can do this is because there are different hydrocarbons inside, and they've got boiling points that are different to each other. So we can separate them into what we call fractions. Okay, and you may have heard of fractional distillation before, and it's an experiment that sometimes you can do in school, and it's very simple. And fractional distillation looks like this. So essentially you get a liquid, and inside this liquid, it's got a mix of different liquids, okay? So we can have like liquid A and liquid B inside here. And now these two liquids, they boil at different temperatures. And because they boil at different temperatures, we can apply some heat and only some of it will come out. So you can see this was green, but we're only extracting some blue stuff. So like only B came out. And the fractional distillation lies on the fact that different compounds have got different boiling points. And that is basically the whole process. So you essentially you apply some heat and then it ends up collecting as a liquid. So this is a very simple diagram, but when we extract crude oil, we do this just on a much larger scale. And this process is fractional distillation. So guys, before we go any further, fractional distillation can get a bit confusing. So I just want to highlight some key principles here as to how it works and why it works in this way. So you will know that here, if we pour some liquid, okay, the liquid is blue, and this is a tripod, so we heat it up. If you heat up a liquid, you will go from a liquid to a gas, right? And this process is evaporation. Okay, so when we go from liquid to gas, we evaporate it and the gas is given off. On the other hand, sometimes you will notice on your window, if it's a cold morning or a frosty morning, you will see that there are some droplets of water that are formed. The reason is because gas has gone to a liquid. Okay, and this is condensation. And this is the opposite. So fractional distillation is relying on both of these processes, and you need to know the differences between them so that you can understand what is happening in fractional distillation. So does anyone have any questions so far? Are you guys okay? Okay, great. So just keep this in mind. And so we saw fractional distillation as that little experiment, but in crude oil, okay, you can see this is a huge industry, and they use these massive machines to try and extract that crude oil. So it's this really long tower and with loads of pipes, and this is actually known as a column. And this is what it looks like in real life. So we're basically going to talk about how they do this. Okay, so this is fractional distillation of crude oil. So basically each hydrocarbon fraction, it contains molecules with similar numbers of carbon atoms. So as I said in the beginning, with crude oil, okay, some of the chains are very long and some of them are a bit shorter and some of them are even smaller, etc. There is a huge difference. Now, the ones that are similar, they tend to group together. Now, each of these fractions, they boil at different temperature ranges, and that is because of the different sizes of the molecules. We said that as you increase the chain length, your boiling point increases, doesn't it? So the molecules that are long, they will need a much higher temperature, okay? And this is the basis of fractional distillation. So I'll just show you, so this is an overview and we'll talk through this step by step. So essentially, this is your crude oil. This is that thick, gloopy substance that we start off with. And we then put it through these pipes and then it separates in the tower into lots of different fractions. Okay, so the first thing that we do is crude oil is heated. Okay, so this is important. We are heating this crude oil and it's fed near the bottom of a tall tower as a hot vapor, okay, so i.e. as a gas. So basically what's happening is you take this crude oil is a liquid, okay, and you basically put it in a furnace. Furnace is like something that is really hot. So the temperature here will be like really, really high. It might even be like 1,000 degrees. So they will really heat up this crude oil. Now, if the crude oil was a liquid and you're going to put it in 1,000 degrees, okay, it's going to turn into a gas, isn't it? So this is evaporation. Okay, so essentially what we are trying to do is we're trying to evaporate the crude oil and turn it into a vapor, i.e. a gas. So you feed your oil in, you put it in this massive burning hot furnace, and essentially it turns into a gas at this point. Okay, so our liquid has turned into a gas over here. Now, in terms of the column, when it gets to this column, so this column is very clever. At the top, it's very hot, okay? So I'm sorry, at the bottom, it's very hot. So you can see that it's 350 degrees or even more at the bottom. And as you're going up, the temperature is actually much cooler. So it's only 25 degrees over here. So it's like room temperature, okay? So it's kept hot at the bottom and much cooler at the top. So as you go up the column, the temperature decreases, okay? As we're going up, the temperature will decrease. Now, what is happening? So remember, we had our crude oil as a liquid, we heated it up, and we turned it into a gas. Now, what's going to happen to this gas is as these gases are rising up, okay, the temperature is changing, and the point at which they reach their boiling point, they will then go back into a liquid, okay? So in the tower, the crude oil gas is going into a liquid, okay? This is condensation. And essentially it will come out as a liquid. So if I put in, let's say, for example, one hydrocarbon and its boiling point is 60 degrees. So when it hits 60 degrees, it will think, okay, this is my boiling point, and it will go back into a liquid and it will just come out of the tower. And we call this naphtha. So these are the different oil, these are the different fuels that can come out of crude oil. Okay, so the different fractions, i.e. the fractions are just basically the different hydrocarbon lengths. And these are collected as liquids, okay, because we have condensed them by changing this temperature, and they're collected at different levels. And these fractions, they're collected in a continuous process. So they don't just switch this on at 9 a.m. and then stop it after 10 minutes, okay? This is happening 24 hours a day, and these machines, they never stop, okay? Because we always need crude oil. So this is just continuously happening as a cycle. So essentially what happens is that if the hydrocarbon is small, okay, they will have a low boiling point. So we talked about this earlier. If we take our methane, okay, remember, this is a very small chain. So it will have a low boiling point. Because obviously you don't need much energy to break these bonds, okay, it's very easy. So if it's got a low boiling point, okay, do you think that it will come out at the top of the tower, or do you think it will come out at the bottom? Just put your answers in the chat. Do you think top or bottom? Okay, guys, so a lot of mixed answers. Some of you saying top, some of you saying bottom. Now, okay, well done for trying. Even if you're not sure, great. So if this is small, so remember methane, this is our really simple molecule. So it will probably only boil at like 20 degrees because it's so small and we can just boil it at room temperature. Okay, so obviously if its boiling point is only 20, so you can see here that at the bottom here, this is for very long chains, this is 350. So only when it will climb all the way up as a gas, and only when it reaches its boiling point at 20 degrees up here, it will then go from a gas to a liquid, okay? And then it will come out over here. and then we have petroleum gas. This is what we really like to use as a fuel. So the hydrocarbons that are small, they have low boiling points, and they are piped out of the cooler top of the column as gases. Okay, so they will just come out right at the top over here. Sometimes they can come out as a gas, but usually they will also be converted into a liquid. Okay, and then at the bottom of the column, okay, the fractions have got high boiling points. So remember, crude oil is a mixture of substances. So if we take our very long chain, okay, so we just imagine that there are hydrogens as well here. So this is a very long hydrocarbon, okay, and this is going to require a lot of energy to break up all these bonds. So my boiling point here will be high. Okay, because I've got a high boiling point, I need a high temperature for this to be condensed. So these long chains, okay, because they need such a high temperature, it's hot at the bottom, isn't it? So these long chains, they will stay at the bottom, and they will cool to form very thick liquids, or even sometimes they are solids. Okay, they condense to form solids because they're very gloopy, and they require a very high temperature. So they will just come out right at the bottom. And once collected, the fractions need more processing. So we don't really like these long ones, and we'll talk about why, but they're a bit annoying because we actually have to break them up even further. Okay, guys, so at the top of my column, I will have my short chain that will come out, and at the bottom, I will have long chain. Okay, these will have a low boiling point, okay, because the temperature at the tower, at the top of the tower, is cool. The longer chain ones, these will have a high boiling point because the temperature is higher at the bottom. Okay, you can see that over here. All right, guys, so just a recap of this whole system. So remember, in the beginning, I take crude oil. This is a mixture of hydrocarbons. Okay, some of them are short and some of them are long. I take this crude oil, okay, and I put it inside a furnace. So I'm literally going to put it on fire, and the temperature here is really very high. So my oil will turn from a liquid to a gas, and it will evaporate. Okay, so now I've got a lot of gas over here. We then move to my fractionating column, or we can call this a tower. Okay, now this tower is hot at the bottom and it is cold at the top. Okay, we've got a lot of gas collecting here, and essentially this gas, it will condense at its boiling point. Okay, so the gas will go to a liquid when it reaches its boiling point. So so obviously the molecules which are short, they will have a low boiling point, and the molecules which are long, they will have a high boiling point. So therefore you will appreciate that the molecules that are long, they will be at the bottom, okay, because they require a very high temperature to condense and to come out. And the molecules which are short, which have a low boiling point, which are very simple, they will be at the top. Okay, and that is basically what fractional distillation is in a nutshell. And then I just want to draw your attention to all of these things here. So there are a few main oils that we can take out from crude oil for our uses. The one right at the top, the short chain, is petroleum gas. And petroleum gas is basically petrol. Okay, so this is what we put in cars as a fuel, and this is very valuable. We really like this because obviously we need a lot of this. Now, as you go down further on, you will see that there are some other fuels like diesel, which we sometimes use in cars, but also in larger things like trucks, and fuel oil for ships. But as we come further down, remember these compounds here, they're very thick, and they are a liquid, and sometimes they can even be a solid. Okay, so we have something called bitumen or bitumen, and this is basically like what they use in road surfacing. So if you ever go out and you see them doing road works and they putting like all these black bits on the road, this is basically what they're using, and it's a very thick substance. Obviously, we can't use this as a fuel, okay, because we want small chains for fuel. So just try and familiarize yourself with you don't need to remember these names, they tend to give it to you, but just remember that at the bottom, these tend to be much longer chains, and we have different uses for them. So at the top, we may use these for fuels, and these have other uses like for road surfacing. And sometimes we actually need to break these down because they're too long, and we will talk about that. So guys, do you have any questions about fractional distillation? Because I know it's a bit difficult, especially if you've not met this concept before. Okay, let's see what you guys have said. Okay, so let's just do a quick question then, just to test you guys. Okay, so let's have a look at this. Okay, so this is from the exam. So crude oil is a mixture of many different carbon compounds. Crude oil can be separated into useful fractions by fractional distillation. Figure 2 shows a column used to separate crude oil. So guys, this is basically what we just saw. And it says complete the sentences. So use words from the box. So crude oil is heated so that most of the compounds. Okay, so guys, I want to make sure that everybody knows what I'm talking about. So I'm just going to label this. So let's just say A is condense, B is evaporate, and C is freeze. So I want you guys to vote. What do you think is the first answer? A, B, or C? So crude oil is heated so that most of the compounds. Okay, so pretty much all of you have said B, evaporate. That is fantastic. I'm really pleased with that. Well done, guys. So remember, we evaporate it first. We take that liquid and we turn it into a gas over here. Okay, well done. And then what do you guys think is next? So at different temperatures, the compounds, they will cool, and A, B, or C? Great, amazing. So they will condense, won't they? At different temperatures, the compounds will cool and they will condense. Okay, so for those of you that said freeze, so remember, freezing is when we turn from a liquid to a solid, and that is at cold temperatures, like for example, when you are freezing and it is snowing outside. This column is burning hot. Okay, so freezing is, there is nothing to do with freezing here. It can either only be condense or evaporate. Okay, well done, guys. So let's have a go at another one. So this is the same question. So crude oil is a mixture of many different compounds. Which fraction is the most viscous? What do you guys think? So we touched on this earlier. So A, B, C, or D? Okay, guys, so most of you have said A, but we've got a few mixed answers. So let's talk about this. So when we talked about our definition for viscous, okay, this is how thick it is. Okay, remember that picture of honey and water. So the ones that are thick, okay, they will be long, and the ones that are runny, they will be shorter chains. Okay, and we know that at the bottom the chains are short. Okay, and sorry, we know that at the top the chains are short, and at the bottom the chains are long. Remember that this is a simple fuel that is short, and at the bottom we have all that residue and tarmac, which is long. Okay, so the ones that will be the most viscous will be the ones that are longer, so they will be the ones at the bottom. So it can only be residue or engine oil, and they've put engine oil here, so engine oil is the correct answer. Okay, hopefully that one makes sense. Okay, which fraction is the most flammable? Okay, most of you have gone with D, so that would be refinery gas. So remember, flammable is how easily it burns. Okay, and we know that if the chain is short, it will burn easily, and if the chain is long, it will be harder to burn, right? We know at the top we've got short chains, and at the bottom we have got long residue, and therefore the most flammable will be the one at the top. Okay, so that would be refinery gas. So that is amazing. Well done. Okay, and guys, just one last question on crude oil. So we've got a bit of a harder question here. So let's just look at this one together. So again, you can see they're given the similar diagram. Crude oil is separated into useful fractions by fractional distillation. Okay, and the question is now saying describe and explain how crude oil is separated into fractions by fractional distillation, and use the diagram to help you answer your question. So guys, for this type of question, so it's given us two key words. So describe means that you just want to state the facts and what you can see in the diagram and your observations. When it says explain, you need to give reasons, okay? So what you've said in your describe it, you need to say why that is true and why that happens, okay? We've got a 4 marker, so we want to say 4 different things. So I'll just give you guys a couple of minutes to jot down your answers. Feel free to put it in the chat and I can critique and help with your exact answer as well. So what's the first thing you want to say, guys, when you start this off? Obviously, you want to say what happens in sequence. So just tell me, what do you think is the first thing you'll write down? Great, so some really good answers. So the first thing that we want to say in the bottom, we want to say is that we start off. So we start off over here. Okay, so you can say that crude oil is heated in the furnace. Okay, and we want to use our key terminology that we know. Crude oil is heated in the furnace and evaporates, okay? So you want to say that it evaporates or it is turned into a vapor, okay? Because that is the principle behind it, in that it has evaporated, okay? So we can say that, we can then say that the vapor, you can say it cools as it rises to the top, or you can say that the column is cooler at the top. Okay, and then we want to talk about with the fact that we know that hydrocarbons, they have got different boiling points. So you can say that the fractions have different boiling points or different condensation points. And therefore, because they have different boiling points, therefore they will condense at different levels. Okay, so those are sort of the four main things that you want to state. Okay, so can you guys see how we have learnt this whole topic, but really to translate this into the exam question itself, you have to be very specific in what you say. So I'll just show you the mark scheme. So you can see they've said crude oil vaporizes or evaporates. That's underlined, okay? So you want to say that. The vapor cools as it rises, or the column is cooler at the top, okay? There's a temperature difference. And the fractions have got different condensation points or different boiling points, and therefore they will condense at different levels in the tower. Okay, so these two are basically your explanations, and this is a description of what is happening. Okay, great. Well done, guys. So I think we'll do a quick quiz now on fractional distillation, just to make sure that you guys are all following. Okay, we'll get started. The pin is at the bottom if you haven't been able to join yet. Amazing, well done, guys. Boiling point, fantastic. Yep, it's heated. Okay, so a few mixed answers. So what features does crude oil have that allows separation by fractional distillation? So the key
feature is that the boiling points are different, okay? It doesn't matter about this. Yes, they have different sizes, but we want to be more specific. It's because they boil at different temperatures. That is why. It's not to do with their melting point, okay? It's the boiling point. Remember, we are heating things up. This is not cold. It's to do with the furnace, so it's boiling. Exactly, guys. So it's the boiling point. As we just said, it's not the melting point. Yay, it's the bottom. Well done. The top is very cool. It's just about room temperature. Fantastic. Hydrocarbons. Well done, everyone. I'm super impressed. So a lot of you got pretty much everything right. Okay, that's great. So we will just continue from where we left off. Okay, guys, so we have talked about fractional distillation very clearly now. There are a few other things that we want to talk about when we talk about hydrocarbons. So you will remember that basically the ones at the top of the tower, we use these as fuels. Okay, and the ones at the bottom, these are used in tarmac and they are very long and we need to sometimes break them down. Okay, so we're going to move on to talking about how do we actually use what we get from the fractional distillation. Okay, so we're going to talk about something called complete combustion. So we talked about the lighter fractions of crude oil. These are the ones that are most useful to us. And these form our fuels in petrols, in engines, airplanes, etc. Now, when we use that fuel, basically what is happening is that we are having a combustion reaction. Okay, when we use that fuel in our car, this reaction is taking place all the time. Now, when hydrocarbons, if we burn them in plenty of air, so if they've got lots of oxygen, a lot of energy is released into the surroundings. Okay, and this is known as an exothermic reaction. So we covered this. This is not really the subject of today's talk, but exo meaning out, thermic meaning heat. So these reactions, they give off a lot of heat. Okay. And basically the carbon and hydrogen in the fuel, they are oxidized completely, i.e. they give off oxygen. They are oxidized themselves when they burn like this. Okay, so very commonly we can get asked to write out what the equation is. So if I take a simple molecule like CH4, okay, and I burn it with oxygen. So CH4 is methane, it's a fuel. And I react it with oxygen so that I can burn it. It releases a lot of energy. And two products that it releases are carbon dioxide and water. Okay, and this is a combustion reaction. It doesn't matter what fuel you use. Whenever you react one of these with oxygen, you always get carbon dioxide and water. Okay, and you also give off a lot of energy as heat, and that energy is used when we burn the fuel. So you'll realize that actually this equation is not balanced. So we just need to balance this. So let's do this one together. So I've got one carbon on the right, on the left, and I've got one carbon, sorry, on the right. And I've got 4 hydrogens, and I've only got 2 hydrogens here. So let me put a 2 here. Now I've got 4 oxygens on this side, and I've only got 2 here. So I'm going to put a 2 here. Okay, so this reaction is known as a combustion reaction, and you will always get CO2 and water. Okay, I can put methane, ethane, propane, I can put whatever fuel I want, I will still get these 2 products. So you can see that very clearly here. We've got methane plus oxygen giving carbon dioxide plus water. And just to draw your attention, this is complete combustion. So this is when we have got enough oxygen. Okay, so if you do it in open space, if you do it in air, obviously we've got enough oxygen around, so this reaction can take place. Now, sometimes, which is actually what happens most of the time, is that we undergo incomplete combustion. So obviously, if this reaction is taking place like in a car, okay, this is happening inside the car, and there's not always enough oxygen inside the car in the engine, because obviously it's not an open space. And when there isn't enough oxygen, e.g. in an engine, we have something called incomplete combustion. So it hasn't gone to completion. So again, let's just say we have methane, but this time we're inside a car. So we've got methane, we react it with oxygen, we've got some oxygen, but actually we don't have enough. And if we don't have enough, we don't get carbon dioxide. We actually form something else called carbon monoxide. Okay, so mono meaning one and carbon dioxide is two. So because we didn't have enough of this to begin with, we form something else called carbon monoxide and we still get water. Okay, so I've got CH4 plus O2. Carbon monoxide is known as CO. Okay, it's not CO2 plus H2O. This one becomes a little bit more tricky to balance, and I don't think you will be asked to do this, but basically I can just show you guys. So if I've got 4 hydrogens over here, and I've got 2 oxygens on the left, so if I just put a 4 here, I'll have 8, and then I'll have 2 carbons on this side and 2 over here, and then I'll be left with 6 oxygens here, but I've only got 2 here, so it's 3. Don't worry about balancing this one. You only have to know how to balance it for complete combustion. But basically the take-home message here is that if you burn a hydrocarbon with limited oxygen, okay, such as in an engine, you will produce carbon monoxide. Okay, and carbon monoxide is actually quite toxic. So you may see like in movies, or sometimes like if there's a fire in somebody's house, then the people that are inside, like they start coughing a lot and they start to become very sick. And this is basically because there's a lot of carbon monoxide in the air, and the carbon monoxide is very toxic. So this is sometimes cars can give off some very dirty fumes, and that contains carbon monoxide. Okay, so let's just have a go at doing this one together, because this is usually what we can get tested on. So write a balanced equation for the complete combustion, i.e. we have got enough oxygen, complete combustion of ethane, so that would be C2H6. So we know that with ethane and oxygen, when we have complete combustion, we form carbon dioxide and water. So ethane is C2H6. So if you guys do this on your paper as we go along, oxygen is O2, carbon dioxide is CO2, and H2O. Okay, so how are we going to balance this one? So this one is a little bit tricky, but the best way to do this is to just count how many you've got on each side, and just do it with trial and error, really. So I've got 6 hydrogens here on the left, and I've got 2 hydrogens on the right. So basically, because I've got 6 here, what I'm going to do is I think I'm just going to put a 6 over here. That would be the best thing. But so that would give me 12, and then I can put a 2 here. So now my hydrogens are basically balanced. I've got 4 carbons over here, so I'm going to put a 4, and then that leaves me with oxygen, and oxygen's on its own, so I can put whatever number I want. So I've got 8 plus 6, which is 14. So that means that I will have 7 oxygens here. So this is a little bit tricky, guys, but it just comes with trial and error of just putting in different numbers and seeing what works. Okay, and that is the correct answer there. Okay, so let's just have a go. Another one. So petrol contains octane. Complete the word equation for the reaction of octane with oxygen. So obviously, if they're not telling you about, is it incomplete combustion, but you can just assume that you've got enough. So we know that this is a combustion reaction. So guys, what two products am I going to form? If you just put it in the chat, what do you think? Exactly. So the products that we always get, it doesn't matter that you've got octane, okay? You can put methane, you can put butane, whatever you want. This reaction is generic and it's the same for all of them. So again, I'll form carbon dioxide and water. Okay, great. So guys, we've talked about what we do with the products of fractional distillation at the top of the tower. But basically, you guys will remember that we've got the ones at the bottom of the tower as well, okay, like bitumen, and which is used for tarmac and road surfacing. So we don't usually find this very useful, okay, because it's got very limited uses. It's very thick and it's almost like a solid, okay. So what we want to do is we want to try and make this more useful, and we want to try and get it into something small, because this petroleum gas is very useful for us. So very commonly we can actually break this down and make it into a smaller molecule, because this one is really, really long. Okay, so we're just going to talk about that now. So we've talked about how we burn the fuels, and we'll talk about what we do. So the ones that are very long, okay, we crack them, okay, and this cracking is basically just breaking it up into smaller bits. And the reason why we do this is because it's helpful for us, because the shorter chains are more useful. So essentially we get a long hydrocarbon that comes out at the bottom of the tower, okay, and it looks like this. And basically we break it down into a smaller compound like so, okay? So why are we cracking hydrocarbons? So as I said, some of the heavier fractions of crude oil, they are not high in demand. There's only so much tarmac and road surfacing that we can do, okay? We don't really need it as urgently. And the hydrocarbons in them are made up of large molecules. So these are the ones at the bottom of the tower. Okay, they are large and they are long, like the one over here. And they are thick liquids or solids, and they've got high boiling points. Okay, so these properties are quite undesirable for us. And they are difficult to vaporize. So you can't take this bitumen and turn it into a fuel. Okay, you can't start putting this in your car to use it as a fuel. It won't work, because it's basically almost a solid. So it's a poor fuel. So this is essentially what we do. The best way that we can deal with this problem is by cracking them. Okay, so the larger, less useful hydrocarbon molecules, we break them down into smaller ones, and we call it cracking. So you can see that here. This is our long chain, and essentially we are just breaking it up into smaller bits. Okay, and that is the basis of cracking. Okay, so how do we do this? So just like in fractional distillation, we saw those large towers. Sorry, it's basically the same thing. So cracking is a huge industrial process, and they do it similarly in big sites like this, okay? And it takes place in something called an oil refinery and in these big steel vessels. Okay, so how do we do this, and what exactly do we do? Now, if we want to crack that really long chain, we need to give it some energy. It's not going to want to break on its own. So what do? We heat it. Okay, so just like in fractional distillation, so don't get mixed up, but basically we're going to heat this. So this vapor that we get, okay, so in the cracker, a heavy fraction, so i.e. a long chain, we will think of that tarmac, okay, is heated to vaporize the hydrocarbon. So we're just going to apply heat to this very long hydrocarbon chain. Once you heat it up, it will turn into a vapor, i.e. a gas. And what you can do is you can pass it over a hot catalyst, or you mix it with steam and you increase the temperature. So a catalyst is something that speeds up the rate of the reaction. And basically, if you mix it with steam and you heat up the temperature, essentially all we're trying to do is we're just trying to give it some energy to try and break down, okay? So these are the two things that we can do to just try and help break down that compound. So either we can pass it over a catalyst, or we can mix it with steam and really just burn it up. It's sort of like the furnace that we put the main crude oil in, but basically it's just about heating it up. So now this process that breaks down this long chain into a shorter chain, this is known as thermal decomposition. So thermal meaning heat, and decompose meaning breaking down. Okay, so we are using heat to break down our long chain. The large molecules are split apart to form smaller, more useful ones, and we call this thermal decomposition. So cracking is an example of thermal decomposition. There are many thermal decomposition reactions in chemistry, and cracking is one of them. Okay, so let's just look at a really specific example. So here I've got a very long chain. How many carbons have I got here? I've got 10. Okay, this is very long, and this is called decane. You don't need to know the name, but it's basically it's quite a long alkane molecule. Now, this is not useful for us. I actually just want a really small bit of it. Okay, let's just say I actually just want this because this is a very small hydrocarbon and I can use this as a fuel. Okay, so how am I going to get that out? What we will do is we will heat it up. Okay, and we will put a catalyst on there, just like we've said. We will do thermal decomposition. And we will break it up. Okay, and what if we break that up? Basically, we will be left with two parts. So I'll be left with one bit that has got 2 carbons and another bit which has got 8 carbons over here. Okay, so I basically will split this up into 2 and we will just crack it over here. And then one of the molecules produced is octane. This means it's got 8 carbons over here, and we can use that one in petrol. And then we also make something else called ethene, okay? And I will show you guys what this is, but this is really useful. We use this in plastics. Okay, so basically, let's just have a look here. So this is my long alkane, okay? And I want to break it down. So let's just say I want to cut it over here. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8 carbons here. So this is my shorter chain. I can put this as a fuel and I can use this in petrol. And then you can see that I'm left with this other molecule, which has just got 2 carbons. Okay, now, because there are only 2 carbons, it's actually a bit different, and it's got a double bond. And we will talk about this after lunch, but basically this is an alkene. Okay, it's not an alkane, it's an alkene, and it's got a double bond, and this is really useful. It's basically used in like carrier bags and water bottles and all sorts. And this process is actually amazing, okay, because if you are stuck with a long chain, this is really not useful for us. So it's very helpful for us to apply heat and a catalyst and to thermally decompose this, okay, thermal decomposition. And I will be left with a short chain alkane, and I will also be left with an alkene, okay, and we will come on to talking about this now. So when we crack hydrocarbons, i.e. break them down, we form a shorter chain alkane and another type of molecule. Now this other molecule, as I've touched on, okay, this has a name that ends slightly differently, and they end in ene. Okay, this type of molecule is called an alkene. So this is different. It's not an alkane, and this is why you have to be really careful with your spelling, because if you make a spelling mistake, you won't get the mark right. So the different ending tells us that these molecules are unsaturated. So basically what that means is that they have got spaces to add on more molecules. Okay, we can contrast that to the alkanes, which were saturated. Now, the reason that they're unsaturated is basically because they've got a double bond. So you saw that the alkene has got this structure and the alkane has got this structure. Okay, this is an alkene and this is an alkane. Remember, carbon can only form 4 bonds, so we'll have 1, 2, 3, 4 over here. So I'll just show you guys that. So these alkenes have got a CC double bond in their molecules. And don't worry about all of this text, but basically, as carbon atoms form 4 covalent bonds, it means that unsaturated alkene molecules, they've got 2 fewer hydrogen atoms. So I'll just show you guys. So this is ethane, and we have got 1, 2, 3, 4, 5, 6 hydrogens, right? We've got 2 carbon and 6 hydrogen. Now, if I draw ethene, basically, because I've now got a double bond here, okay, and carbon can only form 4 bonds, it means that I can only draw 2 hydrogens. Okay, so this is 1 bond, 2, 3, and 4. Can you guys see that? Again, this is 1, 2, 3, and 4. So I've got 2 carbons, but I've only got 4 hydrogens here. And this is a key difference. So ethane is saturated, but ethene is actually unsaturated, and that means that basically, because there's this double bond, I can actually add on another hydrogen. It gives me some room, and I'll show you guys this later. But basically, in cracking, okay, you will form 1 short chain alkane, and then you get this ethene, which is this extra molecule. Okay, guys, so I think we will just do a quick quiz on cracking, and then we can go for our lunch. Fantastic, guys. So you need both. You need a catalyst and you need a high temperature. A catalyst speeds up the rate of the reaction, and the high temperature gives it that energy. You need both of them. Okay, guys, so a few mixed answers here. So I will go through this at the end so you guys are clear. Great. So we're making smaller hydrocarbons. Fantastic. So we're breaking larger hydrocarbons into smaller ones. That's the whole purpose. Yep, so guys, this one is ethene. We will talk more about this molecule. It's not ethane because there's a double bond. Methane is not real, and bute is, remember, monkeys eat peanut butter, so it would have 4 carbons, and that one only had 2. Fantastic. So with cracking, okay, we get 1 alkane and we get 1 alkene. Well done, guys. So just before we go, I just want to quickly show you guys this. So if you guys look at this image, okay, so this is a long hydrocarbon, and in cracking we are trying to break it down. Okay, so whenever we break it down, we will be left with an alkane, which is shorter. Okay, so we've got 1, 2, 3, 4, 5, 6, 7 hydrocarbons here, 7 carbons, and we've got 5 here, and we are left with a shorter alkane, and then we are left with something known as an alkene. Okay, this has got a double bond, and this is just how it breaks. If you were to cut it off, you lose out on 2 hydrogens, and that's why you form an alkene. Okay, so it doesn't matter which specific ones you get, but whenever we go from a long chain alkane, we get 1 alkane and we get an alkene molecule. Okay, so that's why this answer here, what are the products of cracking a long chain hydrocarbon? Your correct answer would be you get this 1 alkene and then you get a shorter chain alkane. Okay, it cannot be, these are all wrong, all of the other ones. But we will recap this again after lunch. But well done, everyone. So we'll go for a lunch break now. And if you guys can come back at 1 p.m. and we will continue. If any of this didn't make sense, please just leave it in the chat and I'm happy to go through it as well during the break. Okay, otherwise enjoy your lunch break and see you soon. Hi everyone, welcome back. So I hope you enjoyed your lunch break. We are going to be moving on now and talking about what we sort of touched on just before, which is alkenes. Okay, so you will know that basically when we had our crude oil, okay, it's basically made up of lots of different alkanes. Okay, and these molecules are saturated hydrocarbons. And we said that they are usually they can be called methane, ethane, propane, or butane. Those are the first four in the series, okay? And all of them have in common is that they have got carbon-carbon single bonds, okay? And all of these are described as alkanes. We then said that if we were to crack an alkane up, a really long one, we would get a side product, which is known as an alkene. Okay, and that's what we're going to talk about. So this one difference in the letter here is actually totally changing our compound. And the way that we distinguish alkanes versus alkenes is this double CC bond, okay? So try not to get mixed up. If we've got an alkane, the bonds are just singular, okay? But with an alkene, they have got double bonds, and we're going to talk a little bit more in detail about these now. Okay, so this is an example of an alkene. And the alkenes all have a CC double bond group of atoms in their molecule, okay, and that is what makes them unique. And we call this CC group, it's an example of a functional group, because actually this double bond, you might not think it's a big deal, but because of this double bond, these alkenes are able to take part in lots of different reactions, and they're actually very reactive because of this double bond, and we'll talk about that now. Okay, so now all of these alkenes, because of this double CC bond, okay, we call this CC bond its functional group, because basically it gives it its function. And any compound that has basically got this double bond, we can sort of group that, we can group them together and call it a family. So any set of compounds that have got the same functional group, and we basically just call them a family, because they will all behave in the same way. It doesn't matter how long it is. In general, because of this double bond, they will all do the same thing if you put them in the same temperature or you mix them with the same reactants. A more fancy word for this family is known as a homologous series. Okay, so a homologous series is basically a family of these organic compounds. And homo means same. So basically they all have the same functional group. So they're a homologous series. And each member in these series, essentially they just differ from each other because we're adding in one more carbon. So remember we saw with methane, ethane, propane, butane, essentially in each one, we're just adding on one more carbon, but those were the family of alkanes. And now we're going to look at the family of alkenes. Okay, so you will remember that with alkanes, their general formula was CnH2n plus 2. Okay, that was for an alkane. Now with alkenes, it's slightly different. It's actually a bit easier. So the general formula for an alkene is CnH2n. Okay, so if we look at our example here, so this has got 2 carbons. So remember we have monkeys eat peanut butter. So 2 carbons brings me to E. So I know this will be eth something, and because it's an alkene, this is ethene. Okay, we've got 2 carbons, so it would be C2H4. Okay, and this is the simplest one. We don't have we don't have anything beginning with methane in the alkenes, because obviously this is a double bond, so you can't just have one on its own. So it starts off from ethene. There is no such thing as methane. Okay, and alkenes have all got this suffix -ene, okay, in contrast to alkanes, which have got the suffix -ane. Okay, so let's just go through a few examples now. Okay, guys, what do you think this one is? Fantastic. So I did give you guys the answer. So this one is C2H4, and this one will be ethene. Well done. Okay, and then what do you guys, does anyone know what this one might be? Great, so this one is propene. Well done. So because we have got 3 carbons, okay, this one will be propene. Okay, and then last one, do you guys know what this one would be? Fantastic. So all of you guys have got that. That's great. So this one is butene. So just remember that all of these here, these are alkenes. My general formula is CnH2n. And you will remember monkeys eat peanut butter. Okay, so and this is 1, 2, 3, 4. So if I have got 2 carbons, okay, I will be on eth, and they all end in ene. So this will be ethene, C2H4. I've got 1, 2, 3 carbons, so it's going to be prop, and this is an alkene because I've got a double bond. This is propene, and it will be C3H6. And now I've got 1, 2, 3, 4 carbons, so I know it's going to be monkeys eat peanut butter, so it will be bute, and this is an alkene because of the double bond. So this is butene, and it will be C4, and 4 times by 2 is 8, so I've got C4H8. Okay, so those are our basic ones, and these are all alkenes because they've all got a double bond. Okay, great. So those are our answers there. Okay, guys, so this is a bit of a challenge question. Does anyone know what this molecule might be called? So this is a little bit extra, but put it in the chat if you know what this one is. Fantastic, you guys are doing really well. So here I've got 1, 2, 3, 4, 5 carbon atoms, and the name. So we've only done the first 4, but the naming them after 5, 6, 7, 8 is actually really easy. So because it's 5, we just think of our pentagon, which has got 5 sides, and a pentagon begins with pent. So this is also going to be called pent, and because there is a double bond, we call this one pentene. Fantastic, and it's actually really easy to name them afterwards. So if you had 6 carbons, it's hex, 7 is sept, and it's just based on their shape. So it gets easier. Okay, fantastic. So let's just do, sorry, quick question. So draw bonds to complete the displayed structure of ethene. So I've got eth, 2 carbons, it's ene, so it's an alkene. So I know I've got to put a double bond. So this should be nice and easy. So the answer would be like so, okay? And carbon can only form 4 bonds. So you do not need to start drawing any other hydrogens or anything like that. That is wrong, okay? We've just got 1, 2, 3, 4 bonds here, and that is ethene. Okay, so guys, now that we've got the basics very clear, we're just going to talk a little bit about how these alkenes react, okay, because it's very different to the way in which our alkanes reacted. Now, it is the carbon-carbon double bond, which is that CC, that makes the alkenes far more reactive than the alkanes. Okay, so you might not think this is a big deal, but actually the presence of the CC bond means that the ethene is much happier to react with other chemicals because this bond can be easily broken. Whereas because this is all full, okay, if I try and add something, carbon can only form 4, so it doesn't want to do anything, it's already stuck. Whereas here, if I want to add something, this double bond can break and we can add on another single molecule, okay? So alkenes are more reactive. And why is that? Because they've got this double bond. So they tend to take part in things called addition reactions, which is basically just adding things on, okay? So you can see that very clearly over here in this diagram. So this is an alkene, okay? So we've got our double bond here, and these gray ones are just the hydrogens. We can get another molecule that's just like this, and because of this double bond, this bond is quite weak and it's very easily broken. So the CC double bond will open up and the molecules will add on. So can you guys see that these purple bits, they basically came over here. And then this became a single bond. Okay, that is what happened over here. So now this is saturated. There is no double bond over here, but this reaction can take place, okay? And there are many addition reactions. There are 3 main ones that we will cover, but it doesn't matter what this is, okay? So just keep this general principle in your mind. This can be hydrogen, this can be chlorine, it can be bromine. It doesn't matter. Whatever it is, it will literally just slide in over here, and this will become a single bond. This is a way of adding on a chemical, so we call it an addition reaction. Okay, so let's look at a few examples now. So the first one is alkenes will very readily, they will react with halogens. So halogens are elements that are in group 7 of the periodic table. Okay, so if you look at your periodic table and you go to group 7, you will see that we have got chlorine, bromine, and iodine in order. Okay, and they all belong in group 7. Now, very commonly, as I've said, so alkenes are generally more reactive than alkanes. And the reaction with bromine water is really common, and it's a very fun experiment actually, because the color change is very obvious. So you can use bromine water if you've got a compound, if you've got like a liquid and you're like, oh, I don't know, is this an alkane or is it an alkene? You can put bromine water, which is Br2, and this is in group 7. And you just put this bromine water in there and you will see a very significant color change if an alkene is present. Now, so a positive test for an unsaturated hydrocarbon, i.e. an alkene, is that it turns the orange bromine water to colorless. And alkanes, because they are saturated, they won't do anything with the bromine water. So this test can be used to distinguish between an alkene and an alkane. So basically what you guys will see over here is, so bromine water is naturally orange. Now, if I pour this bromine water on, let's say I pour it on ethane, okay, and I try and bring in this Br2 molecule here, ethane doesn't care, okay, it's going to do nothing with this. You can leave it for hours in the mixture and nothing will happen. It will remain orange, okay. If on the other hand, I've got ethene, okay, and I put in bromine, immediately what will happen is that this alkene is very reactive, and you will see that it will mix together, and I'll show you how, and then the bromine water will change from orange to colorless. Okay, and this is a very nice experiment because it happens over seconds and you can immediately see that color change. So I'll just show you guys what that looks like, okay? So you can see here, so this is ethene. Okay, we know it's ethene because we've got a double bond. This is bromine water, Br2. And just like how we saw in the beginning, all that will happen is that these two Brs, they will come and sit themselves at the bottom, and essentially you will get this compound. Okay, so this double bond will become single, and we can then add on 2 more bits. We can add on these bromines and you will get this structure. Okay, so this is orange and this is colorless. So when we react ethene with bromine, we then get ethane, okay, because it's now become an alkane because it's a saturated compound. And this is a little bit extra, but we call it dibromo. Bromo comes from the Br2, and di is because there are two bromines, so we call it dibromo and ethane. Okay, so if I were to write that out, it would be C2H4 plus Br2 with basically, then you can just literally write it out like this. So C2H4 and then Br2 because they've all added on together. Okay, so this is an addition reaction. Okay, so that is the first type of addition reaction that alkenes will do. Okay, guys, so just a quick exam question just to check that you guys are awake. Okay, what is the color change when bromine reacts with ethene? Is it A, B, or C? Okay, amazing, guys. So everyone has got that correct. So it goes from orange to colorless. Okay, this is a nice, easy 1-mark question that you don't want to miss out in the exam. Okay, and yeah, okay. So that was the reaction with halogens. The alkenes, they very readily react with hydrogen as well. So hydrogen is H2. Now we've said that the alkenes are unsaturated compounds, and because of that CC bond, that double CC bond, their molecules do not contain the maximum number of hydrogen atoms. We can still add more. Okay, that's the definition of unsaturated, is that we can still add more. Okay, so what happens when we add hydrogen to ethene? So let's just say, so I take ethene. Okay, and I react this with hydrogen. So, okay, so this is hydrogen over here. And basically, what do you guys think will happen? So have just a couple of seconds to just draw this on a piece of paper as well, so you can check if yours is correct. So I've got ethene here, and I've got hydrogen. And basically what will happen is this double bond wants to break, okay, and these hydrogens want to try and attach to it. So my double bond will break, and I will get these extra hydrogens being added on at the bottom. So I'll have a hydrogen and a hydrogen. These are these two new ones that have come on. Okay, and then my regular ones that were there, so these 4 will stay here as well. Okay, so I'll have these hydrogens here. So overall, the compound that I will form is going to be what? It's C2H6, right? And that is ethane, which is an alkane. So this is saturated, and this one was unsaturated. Okay, so hopefully you guys got that one as well. Now, this process is just shown here again. This is the exact same thing. This process is actually called hydrogenation because we are basically adding hydrogen. And you might think, what's the point of this reaction? But actually, this reaction is what we use to make margarine. So this is done in the industry a lot because the addition of hydrogen to ethene gives us something that we add to margarine. So this is a very useful reaction that we have. And it won't just happen on its own, okay? Because hydrogen is not, it's not going to just react with it. We need to do a few things. And very commonly, we need to add a catalyst to speed up the rate of the reaction. And we normally use a nickel catalyst, which is a type of metal, and that's just the one that works best. So we use a nickel catalyst, and it needs a high temperature of around 150 degrees. So they do like to ask this. So when we are trying to add ethene to hydrogen, we use a catalyst of nickel, and we use a temperature of 150 degrees. Yeah, so for this reaction to take place, we need a nickel catalyst and we need a high temperature, okay? And we are going from an unsaturated ethene to a saturated ethane. Okay, guys, and then just finally, one last addition reaction that ethene, that any alkene can do, is that of a reaction with water, which is basically steam. Now, if we react ethene with steam, we get something called ethanol, which you can see over here, and this is an alcohol. So if we react C2H4 plus steam, which is water, we basically will get ethanol, and the way we write that out is C2H5OH. This is the alcohol group, and we will talk about this. So essentially, this ethanol is really important. We can use it as a solvent to dissolve things, or we can even use this alcohol as a fuel sometimes, and also for drinking alcohol as well. And we can make it from our ethene gas. So again, this reaction, it does require a lot of energy. The ethene is not very reactive to do it on its own. We need to supply some high energy and a catalyst as well. So we've got ethene and steam gives us ethanol, and that was C2H4. This is our reaction over here. Okay, guys, so just a quick overview before we move on to talking about something else in alkenes. We've got three main types of reactions, and I want you guys to just jot this down as we do it together. So these are all addition reactions. The first one is when we react it with a halogen. Okay, so we get C2H4, for example, plus that bromine water. Okay, and this will go from orange to colorless. Okay, our second type of reaction is when we react our alkene with hydrogen. And this will give us ethane. Okay, and this is basically used in margarine. Okay, and we need 150 degrees and we need a nickel catalyst, yeah? And finally, the last type of reaction is when we react it with water or we react it with steam. Okay, so again, we take our C2H4 and we react it with water. We will form this alcohol, okay, and we get an alcohol here. So you can see how versatile these alkenes are. Okay, we are making margarine, we are making fuels, we can make alcohols with them. And the reason that we can do all of these things, okay, is purely because of that double bond. Okay, you cannot do any of this stuff with alkanes. It's out of question. We cannot do it. Okay, so alkenes are very useful for us. And this is why we do cracking, so that we can end up with all of these things. Okay, great. Does anyone have any questions on this? Okay, great. So if you guys have any questions a bit later on, please feel free to ask. So within alkenes is something called polymers, okay? And polymers are a really interesting branch of alkenes, and we're just gonna go through that now, and then we have a quiz coming up, don't worry guys. So polymers, now basically, polymers are really cool. And what we've said is that the fractional distillation of crude oil and cracking gives us a large range of hydrocarbons, doesn't it? We get alkanes and we get alkenes, and we can do millions of things with these. Now, crude oil-based products are all around us. Okay, you might think, why do I have to learn about this? But actually, it's literally in our everyday lives for lots of things that we use. So ranging from cosmetics, in plastics and makeup, and also explosives as well. Okay, so you can see that all of these things here, all of these objects are literally using things from crude oil, and even the packaging, not just these plastic lids,
but also the plastic on top. It's all from crude oil. So one of the most important ways that chemicals from crude oils are used is to make polymers. Okay, and we will talk about what exactly a polymer is now. Now, essentially, what happens is poly means many, right? Okay, so essentially, when we have a polymer, we are just linking up lots of different small molecules together to make up a long chain. That is the basis. Now, these small molecules, we call them monomers. So mono meaning one, poly meaning multiple or many. So the huge molecules they make are called polymers. Mono equals one and poly equals many. And by using different types of these monomers, you can basically make various different types of polymers. So essentially, what we're doing is we're going from a monomer to a polymer. So you can imagine that your monomers are just for simplicity, I will say that these are little monomers. Okay, and essentially when I make them into a polymer, I just make it into a long chain like this. Okay, this is the basis of what we are doing in this process. And sometimes this monomer might be ethene. And if I was to make it into a polymer, we call it something called polythene, which you may have heard of. Polythene is basically those plastic carrier bags that you now have to pay 5p for. So this is what polythene is. Okay, so you can just see that over here. So ethene can go to polythene, and there are lots of examples, and we will go through this now. Okay, so as I've said here, so we go from monomers to a polymer, and we call this process polymerization, okay, which is basically in the name. So the most basic polymer that we can make is ethene. So ethene, we've already talked about, is this molecule over here. And this is the smallest unsaturated hydrocarbon molecule, and we can use it to make polythene. Okay, now this polythene is basically this plastic bag. Okay, it's made up of all these monomers, which is quite remarkable. So polythene is a really useful plastic because basically it's strong. Okay, you can put lots of stuff in this bag, and it's also really easy to shape. So we can change the shape of it, and it's very flexible. It's also see-through as well. So these properties, they make it really useful for us to use. So other examples of polythene are, as you can see, basically like some carrier bags, drinks bottles, dustbins, washing up bowls, cling film. All of these are made from polythene, okay, all of these variety of products. And we are basically going from ethene monomer, mono meaning one, to polythene, okay, to meaning many. Okay, another example is, so we heard of propene, right, which was C3H6. So that is, we've got a double bond, and then we've got this molecule. Okay, this is propene, okay, C3H6. So all alkenes can be made into polymers, okay, because of this double bond. I will show you how, but they can literally all go into polymers. So if we've got a monomer known as propene, the polymer is just basically poly in front with propene, okay? So we are going from propene monomers to polypropene, and polypropene is slightly different. And if you're doing triple science, you might be asked to, state the differences and the uses of these. So polythene is like basically carrier bags, and it's quite lightweight. But polypropene is it's actually very tough and it's quite strong. So you can use it in like ropes, in those milk crates that you see, and even in carpets. So this is a much stronger one. And the reason why is because the chain is a bit longer. Okay, it's 3 carbons. This chain is a bit smaller. So there are many polymers that we can make, but these are just 2 of our examples. Okay, so how does this actually happen? So we've said that we're going from a monomer to a polymer, but what exactly are we doing? Essentially, when alkene molecules, they join together, so what happens is that the covalent bond, that double CC bond between the two carbon atoms, essentially it opens up, okay? So this double bond is literally leading to all of the reactions that are taking place. And because it opens up, it gets replaced by a single carbon-carbon covalent bond. So in our monomers, they look like this. But when we go to the polymer, essentially they become single, okay, in a long chain. And in this way, thousands of molecules. So that one carrier bag is literally made up of thousands of chains of these polymers, okay? And the polymer chains, they're basically a backbone because they're like a long chain, which I'll show you, and we call it a backbone. This type of reaction, just like the other three reactions that we saw before, we call these addition polymerization, okay? Still addition because we are still adding things on, and it's polymerization because we're going from a monomer to a polymer. Okay, guys, so this is just basically what it looks like. So at the top here, so this is ethene. Okay, this is one ethene monomer. These are all ethene. All of these are little ethene monomers. Okay, so we call all of these monomers. Now, when we react together, when all of these will react together via addition polymerization, basically what's happening is that we're making this long chain, yeah? We're making this backbone. Now, what's the key difference? Even if you've never seen this before, what is the main difference? The main standout feature that you can see here is that here we've got double bonds. And here there are no double bonds, okay? These are all single bonds. Okay, and this is basically what a polymer is. You will never have a polymer with double bonds here. This is the whole concept, that we basically break these double bonds and we just join them up. Okay, that's basically what we're doing. We get rid of these single bonds and we just join them in a long chain. And that is what gives us our polymer. So these are ethene monomers. And this is polythene. So you just put whatever it is, you put it in the bracket and you put poly on the outside. Okay, so this is exactly what's happening. So remember, the double bond is being crossed off and we are making single bonds. Now, obviously, we can't sit and write this out because there are literally about 1 million of these joining together. So it doesn't make sense for us to draw out this whole chain. Okay, so there must be a better way of doing this. So the way that we can do this is by drawing out just one unit. So when we talk about addition polymerization, you're not just going to sit there drawing all of these out in the exam. There is a better way of showing it. So what we do is we show our repeating unit. So if this is ethene, okay, so this is ethene here, and basically we just put the letter N in front of it, okay? N meaning number of the polymer chain. So we put an N in front of it. Okay, and this will then go to my polymer. Okay, so now this double bond has gone and I've only got single bonds. Okay, and remember it's a long continuous chain, but I'm only drawing one unit. I'm not going to sit there drawing. I'm not drawing all of these. Basically, I'm just drawing like one section, and that is what this is. And then all you have to do is you just put brackets around it. You must put the brackets in the middle of this, otherwise you won't get the mark. And then we put the N at the bottom. Okay, to show that this is N is our number of repeating units. Okay, so let's say, for example, I started off with 100. If N is equal to 100, I started off with 100 ethene monomers, and then I would basically get 100 of this repeating unit. Okay, so we'll have a go at drawing a few of these, but you can just see it here. So this is ethene, and they've put an N here, and when it undergoes addition polymerization,
Okay, you get polyethene, and you get this repeating unit. So these square brackets, yeah, they signify a repeating unit. So, and n represents a large number. So obviously the exact value depends. So if you're just making one plastic bag, it will be a smaller number. But if you make 1,000, your number will be much bigger. And so this is basically what the repeating unit looks like. So we call it a repeating unit because obviously it's just repeating. And there is no point in drawing this all out because these are all exactly the same as each other. Okay, so rather we would just draw one and we call it a repeating unit. Okay. Okay, so just to show you guys here, so this is my monomer, and the repeating unit of this would look something like this. So my repeating unit would be like so. Okay, and then my structure, so you can say that the repeating unit this is my repeat unit, and then the actual structure of the polymer would look like this. Okay, so you put the N here and you put the brackets around it. This is just there to help you out. So you first write out what is your repeating unit, and then you work this out. But in the exams, you need to draw this one. This is not usually, you don't get the mark for this because you want to basically show that you know that this is a repeat unit and that the same molecule is making up the whole chain. Okay, and this is commonly used in bags and sometimes in crates and in boxes. Okay, guys, so let's just have a go at one. So, so we talked about ethene going into polythene, and we also said that propene can go into polypropylene. Okay, but let's just try it. So sometimes you might get an unfamiliar example, okay, but you don't panic. So this is called chloroethene. So it doesn't matter what is joined to it. All we can see is that there is a double bond. So my repeat unit would therefore look like this. So my double bond is gone, and instead I've got all of these bonds here, and I'll have a H, Cl, H, and a H. So that will be my repeating unit. Okay, and you can see that very clearly over here. The structure of the polymer will look like this. So then all you have to do is you just have to draw the brackets around it to show that this is a repeating unit, and then you can put an N at the bottom. And this is called polychloroethene. You may have heard of PVC before, actually. It's a very common type of plastic that we use. It's used in water pipes and also for coating some window frames as well. Okay, guys, so let us just try a quick question now, just to make sure that you guys are following. So let's have a look at this one. Okay, so this question is about polymers, the formation of polythene. So just like how we've done it, they've shown us here, what is the name of this type of reaction? Okay, amazing, guys. This is an addition polymerization reaction because we are adding it on. Okay, fantastic. So that is the correct answer there. Okay, so this compound is used to make a polymer. State the name of this compound. Okay, so I will help you guys out. So if you pick one of these options, this one is a bit tricky. Okay, guys, so some mixed options. So a lot of you said ethene, but some of you said propene. Okay, so let's just have a look at this. So guys, with this one, be careful because basically they've drawn this out in the shape of a monomer, but whenever we have a long chain, you want to count the number of carbon atoms. Okay, so I've got 1 carbon, 2 carbon, and I've got 3 carbons. Okay, so remember, monkeys eat peanut butter, and we've got 1, 2, 3, 4. So if I've got 3 carbons, this therefore will be prop, and I know that there's a double bond, so this must be propene, not propane. Okay, so it's very easy to think that this was ethene because you just see this, but actually, if you were to draw this out in the long chain, it will basically look like this. So this C that I'm drawing is here, and it's got H3, right? So 1, 2, 3, and this carbon here is from here. These 2 hydrogens are here. Okay, this is basically what it looks like if you draw it out in full, but when we do polymers, we would just write this up here because we want to focus on the double bond, but you must count how many carbons they are. So that is a tricky question. So well done if you got that one right. Okay, so the correct answer here was propene. And the polymer that we would make is polypropylene, yeah. Okay, and one last question before we do our quiz. So the repeat unit of another addition polymer can be represented as this. Draw a structure of the monomer used to make this polymer. So I'll just give you guys a couple of seconds to do that. Okay, so with this type of question, literally all you have to do, so you know that this is one of the monomers, you want to get the monomer, so you know that the double bond basically must be here. So just to keep it simple, I'm going to draw my double bond, and I can see that there are 4 Fs coming off of it. So these will be gone because I'm no longer, it's just a one monomer, it's not going to be bound to, you know, a whole chain over here. So these are all gone. And then I've just got 4 fluorines. Whoops, so I've got 4 fluorines, so I've got an F here, an F here, and an F here. Okay, so this is tetrafluoroethene, I believe, and because there are 4 fluorine atoms. Okay, so and that is basically it. So it doesn't matter, even let's say they put a Cl here, all you have to do is just change this to a Cl. Just remember the basic structure, that you'll have a double bond and then you'll have 2 other elements coming off each carbon atom, because carbon only forms 4 bonds. Okay, great, well done guys. So we will just do a quick quiz now on polymers. Fantastic, guys. So a polymer is a long chain. Okay, it's not short. It's not a single unit. That is a monomer. It can be used to make a plastic, but it's technically it's a long chain. Fantastic. Ethene is the monomer of polyethene. Okay, that is correct because we've got ethene in the just after poly, so that's right. Exactly. So the reason that ethene can become polythene is because of that double bond. Okay, if it was ethane and it was single bonds, nothing would happen. That double bond makes it reactive, and it allows addition reactions to take place. Okay, so polythene has got single bonds, but that's only because it came from ethene, which has got double. Fantastic. Well done, guys. It's that plastic bag that I was banging on about. Great. Great. So actually, this is a bit of a trick question. Both of these are correct. Yeah, it's made from monomers, but more specifically, it's made from ethene monomers. So yeah, I would say ethene. Fantastic. Okay, I'm glad nobody got that one wrong. So yes, it is ethene. And last question. Fantastic. So ethene converts into polythene by addition polymerization. Okay, we are adding something on and we are making it a polymer. Okay, fantastic. Well done, guys. So it's 1:50 now. So if we just go for a quick 15-minute break, and if you guys come back at 2:05, and we will continue on with our last and final section, which is alcohols, and we'll be doing lots of exam practice. So enjoy your break, and we'll see you back at 2:05. Hi everyone, welcome back. So I hope you enjoyed your break. So we've just got just under an hour to go. So we're just going to be talking about one final module which comes under crude oil and fuels, and then we will be doing lots of questions and a quiz as well. Okay, so we're nearly there. Well done everyone. So we have already covered, as I said, we covered alkanes. Okay, and we covered alkenes. These were saturated and these are unsaturated. Okay, so these are made up of single bonds and these are made up of double bonds. Okay, but the thing is with both of these compounds, the only thing that they have attached to them are hydrogen. Okay, they don't have anything else, and this is why both of these were called hydrocarbons, because they don't have anything else attached to them. Okay, and there are actually other compounds in organic chemistry which involve carbon, but they have got extra things attached to them. Okay, and one of those is alcohols. So alcohols is the last thing that we're going to talk about. Okay, so these are separate from, so alkanes is one group, alkenes is another group, okay, and alcohols is another. All of these are separate families. Okay, so remember we called these families of compounds known as homologous series. Okay, so these are all separate homologous series. We're going to talk about alcohols. Okay, so as I said, alkanes and alkenes, they've got only carbon and hydrogen. Okay, however, there are many more homologous series or families of organic compounds that also contain other types of atoms. And some of them, so they can contain carbon, they can contain hydrogen, but they also contain oxygen. And when they contain these three things, a very common example is alcohols. Okay, so they have got an additional oxygen, and that is what basically changes the whole structure. So the addition of just one single oxygen basically makes it a totally different compound, and it's got totally different chemical properties. Okay, so you might not think it's a big deal, but actually it completely changes the way the compound behaves. Now, we had something called functional groups. So you will remember that the functional group for the alkene was that CC double bond. Okay, that's what gives it its function, and that's what allows it to react in the way that it does. Similarly, alcohols have got their own functional group. Now, if a hydrogen atom is removed from an alkane and we replace it with an OH group, it gives us an alcohol molecule. So say, for example, okay, we all know what this is, hopefully. Okay, this is methane, yeah? One carbon, four hydrogens, all single bonds. M is for monkey. This is methane. How about if instead I said, okay, I don't want to put a H here. Instead, I want to cross this off and I want to put an OH. Okay, what that would give me then is a COH. And this is now a totally different compound, okay? And this is still meth because we have got one carbon, but it becomes methanol, okay? Whenever it's an alcohol, it becomes an ol at the end. So alkanes become ane, alkenes become ene, and alcohols, they will have the ol on them. Okay, so this becomes methanol purely because of this OH group. Okay, so the OH group of atoms is another functional group, and this OH, it makes it behave in very certain ways, and it gives it its properties, as I said. Okay, and you can see that this is alcohol here. So this is alcohol that we can drink. However, there are many uses of alcohol. It's not just what we drink. We will see that it's got a lot of uses in the industry as well. Okay, so let us just have a go now at naming our alcohols. Okay, so this one I've already said, this one will be meth because we have got monkeys eat peanut butter, and this will be methanol. Okay, so if I then go up the chain, okay, and I now attach two carbons, okay, does anyone know what this one will be called? You can just put it in the chat.
Fantastic. So we just get our prefix name. So this will be ethanol. Fantastic. So we've got 1 carbon, and now here we have got 2 carbons. Okay, what about this one, guys? So we are on, we've got 3 carbons here. We've got 1, 2, 3, and we are monkeys eat peanuts. So it would be prop. Okay, so this would be propanol. Okay, propanol. And then finally, our 4th one, if we were to add on 4 carbons, okay, so now we have got 1, 2, 3, 4. And therefore it's monkeys eat peanut butter, so it will be bute, okay? So it's going to be butanol, okay? And that's how we name them. So we've got methanol, ethanol, propanol, and butanol. Well done, guys. Now, when we write out the formula, because basically we just want to try and highlight that we've got an OH group. This is like the main standout feature. So when we write out our formula, basically the way we do it is just to show that there's an OH. So I first label this bit. So I'll say this is CH3 for this bit, and then I'll put an OH. Okay, so immediately, I'm not going to write something like CH4O. Okay, this will add confusion and nobody will know that this is an alcohol. I want to highlight this OH group. So I will label this bit CH3, and then I will put an OH. Okay, so similarly, I can do that here again. So I start off, so this is a CH3 group. Okay, and then this is CH2, and this is OH. Okay, so this is something called displayed formula, and it's very easy to understand what this is, because anyone who sees this will know, okay, there's 2 carbons and there's an alcohol, it must be ethanol. Yeah, so even again, I can do that for each of these. So it's just CH3, CH2, CH, and then OH. Okay, so again, I know that there are 3 carbons and there's an OH group. So this is propanol. And here I've got 4. So you can just write this out as displayed. So CH3, CH2, CH2, and then there's an OH. So when you know that there's an OH at the end, you immediately know it must be an alcohol. Okay, so the other way you can write this out is you can write C2H5OH. That's also fine as well. Okay, so this would be C3H7OH, and this is C4H345C4H9OH. Okay, so all of these are fine, and they are all fine because they tell us that there is an OH group. If you start to write this one out as like C2H6O and you bunch these together, it's not very clear. Okay, if I just saw this, I wouldn't know it's an alcohol. So avoid doing that. Whenever you draw this, whenever you write it out with the OH at the end. Okay, so we all know that you know it's an alcohol. Okay, great. So we are going to talk in particular about one alcohol, and we're going to talk about this one, which is ethanol, because this is the one that is really widely used in lots of different things. Okay, so what are our uses of alcohol? So we don't use alcohol in plastic bags or in fuels. Instead, alcohols, especially ethanol, are a very common everyday product. And ethanol is the main one that is in alcoholic drinks. In particular, beer is essentially just made up of ethanol. Okay, so how do we actually make this ethanol? Where does it come from? Okay, you don't extract it from crude oil or anything like that. Alcohol is actually made in a very different way. So we have 2 ways in which we can make this. We can make ethanol. Okay, so this is making ethanol. So how do we make this? The first thing that we can do is we can make it by fermenting yeast, by fermenting sugars from plant material with yeast. Okay, so if you guys were here for our photosynthesis session last month and respiration, you would have seen that actually we talked about this. So there's a lot of overlap in biology and chemistry. So ethanol is made by something called fermentation, and this is known as a biofuel. Biofuel because we are actually using natural sources to make this, and this is very renewable and great way of making alcohol. Okay, so basically the reaction is that we take glucose, which is a sugar. Okay, so glucose is a sugar that we can get from plants, or we can get it from anywhere. And basically what we do is we use the yeast, okay, which acts as an enzyme to speed it up, and it basically gives us ethanol, and it also gives off carbon dioxide gas. So this is a natural process that happens, and it's very interesting because this only happens without oxygen. So this is an anaerobic respiration reaction basically, and the way that they do this in industry is they put it in these massive containers, and the reason that they put it in these containers is because there is no oxygen. They block off all the oxygen, and the yeast works best when there's no oxygen. So this is a very cheap process to make it. And essentially, so you just put in loads of sugar inside, and this yeast is a fungus and it likes that sugar. So it basically breaks it down into ethanol, which people can then drink. And we also give off CO2 gas. Okay, so we've got glucose in the presence of yeast will break down into ethanol and CO2. Okay, so glucose is C6H12O6. Hopefully you remember that. Ethanol is C2H5OH, and we have got CO2. Don't worry about balancing this at the moment. But essentially you just need to put a 2 here and a 2 here. So the main take-home messages is basically this way of fermentation. Okay, this is a great method because it requires very little energy and it's cheap. Okay, and you can keep doing this. Okay, we can keep getting sugar and we can keep mixing it with the yeast. Does anyone have any questions on this method of fermentation? Okay, great. So that is one way that we can make ethanol. Unfortunately, this is not what we usually do because this takes a long time. Okay, so another way that we do this is actually by, we've already talked about this reaction, but we actually use it by making, by reacting ethene. So ethanol can also be made in the industry from reacting ethene. And remember, we get that ethene from cracking the crude oil. Okay, so this is an alkene, okay, and we've already talked about this. Ethene is our alkene, and it can take part in addition reactions, yeah? And basically what we do is we take that ethene, so we've already talked about this, but we didn't, I didn't tell you guys that we made an alcohol, so we take ethene, and basically we just react it with steam, as we've said. So steam is hot. This is just basically really hot boiling water, and essentially because this ethene is very reactive, everything will just add on and you will get your OH over here, okay, and it will give you ethanol. This is ethanol here. So that we've got 2 hydrogens which basically added on. So we've got 2 hydrogens and 1 oxygen. So 2 hydrogens have come over here and 1 oxygen has come over here. Okay, these 2 were already on there because we've got 1, 2, 3, 4, 1, 2, 3, 4. Okay, so this is an addition reaction. And now the thing is with this is because basically we are using ethene, and this ethene has come from crude oil. And remember that crude oil is a finite resource. Okay, I said that in the morning, in that is something that will get finished. Okay, so we don't have an unlimited supply of this crude oil. It will run out, and therefore this diminishes those supplies. So even though it's very quick and it's very efficient, it's not very good for the environment because we will run out one day. So quite commonly they may ask you to compare this process of fermentation, okay, which is very good for the environment and is much more natural compared to this one, which is diminishing our resources, but is a much more efficient way of getting that ethanol. Okay, so it's ethene plus steam. So this needs to be hot and we need a catalyst. And it will give you, so basically you've got C2H4 reacting with water, and that will give you C2H5OH. Okay, great. So just as we talked about with the alkenes, they have lots of different reactions that are they also undergo combustion. So alcohols can do this as well. And some alcohols, not commonly, we don't normally use them as fuels, but sometimes we can. And they can undergo combustion, which is basically, as we've said, when you react with oxygen and heat. So the use of ethanol as fuels shows that alcohols are flammable. So remember that flammable is how easily it burns or how easily it burns. Okay, so ethanol is used in spirit burners and also as a biofuel in cars. So the reason that it's used as a biofuel is only when you make that ethanol from fermentation. Okay, if you make that ethanol from the steam and from ethene, it's not biofuel because it's not good for the environment. So you don't classify it as a biofuel. It's only if you do it from fermentation. Okay, and it burns with a clean blue flame. So combustion always produces two things. Okay, any combustion reaction, doesn't matter whether you burn an alkene, you burn an alkane, or you burn an alcohol, you can only end up with carbon dioxide and water, yeah? Unless you don't have enough oxygen, in which case you produce carbon monoxide, which is that toxic fume. But otherwise, we've got ethanol plus ethanol plus oxygen. Okay, this is combustion when we've got enough oxygen. It doesn't matter what you use, you will only get two things. We will get carbon dioxide, okay, and we will get water. So I can put methanol, propanol, butanol, whatever you want. You can only end up with these two things, okay? So this is very easy to remember. So I've got C2H5OH. So I'm going to get you guys to do balance one of these. So just to have a go at doing it with me. So you've got oxygen, okay, and I'm going to get CO2, and I'm going to get H2O. Okay, so let me just balance this one. So I can see I've got two carbons here. So immediately, let me just put two carbons here, yeah? And then I've got to balance my oxygen. So I've got 4 here and 1 here. So I've got 5 on the right and I've got 3 on the left. Okay, so I think the best thing for me to do, and if I've got 6 hydrogens and I've got 2 hydrogens here, so it's a bit more straightforward. So if I've got 6 hydrogens and 2 here, let me just put a 3 here. Okay, so now hydrogens are balanced and carbons are balanced, and I'm just left with oxygen. So I've got 4 and 3 here, I've got 7 here. Okay, so, and I've got 3 here. So then that means that if I put a 3 here, I'll now have 7 on this side, okay? So these balancing equations, they come up quite a lot. They just require trial and error. So just count how many you've got on the left and how many you've got on the right and keep balancing until you work it out. But the more practice you do, you'll be able to do it more quickly. Okay, guys, and then finally, one last equation that is very important with alcohols, and you will see it again if you do A-level chemistry, is basically alcohols can react with metal. So we said that alkenes, okay, they like halogens, yeah, like bromine water goes from orange to colorless. These are group 7. The alcohols, okay, they actually really like metals and they can react with sodium. Sodium is in group 1 of the periodic table. It is a metal. Okay, if you open up your periodic table, you'll see it right at the top on the left-hand side. Now, these alcohols react in a similar way to water when you add sodium metals. So you get, it's not a very vigorous reaction. So you get a few bubbles and a bit of steam as being produced as well. So basically what happens is I can put sodium with my alcohol. This is, again, we're just doing it with ethanol for simplicity. And basically what will happen is that this sodium, it really wants to come and join this OH group, and it sort of pushes it out the way. So you then get you get your bit of your alcohol, but it has pushed the hydrogen out the way and it wants to come in, and you get this compound which has got sodium and ethanol as well, and then that hydrogen comes out and it's given off as a gas. So we've got sodium plus ethanol, and it gives us a very interesting compound called sodium ethoxide. Don't worry too much about the name of this. It's called sodium ethoxide, and you get hydrogen gas. Okay, and this is a very unique reaction because the alkenes and the alkanes, they don't react with metals at all because they only participate in covalent bonding. But here the alcohol group adds another dimension, and essentially the metal is very much attracted to it. Okay, so the sodium here, so this sodium basically really wants to join over here. So they get rid of the H and instead the Na comes in, okay, and hydrogen gas is given off. And you get this product called sodium ethoxide. Okay, guys, so that is alcohols in a nutshell. So let's have a go at a question now. So methanol can be used in racing cars as an alternative fuel to petrol, okay? Write the chemical equation for the complete combustion of methanol. Okay, so let's do this one together, guys. So you don't need to write the whole thing. Let's just start off with methanol. What is my formula for methanol? First, tell me that. So if you write it in the chat. Okay, so I'll just help you guys out. This is methanol. It's got one carbon and we've got an OH. So how am I going to write out my formula? Just have a go, even if you've got no idea. You can just put your answer down. Great, it will be CH3OH. Okay, so that will be methanol. And what am I going to react it with? What always happens in a combustion reaction? What do you react something with? And remember, this is complete combustion. Exactly, oxygen. Whenever we are burning something, we need oxygen. Great. So I've got here methanol and I've got oxygen. What two products do I form regardless of the type of combustion? There are only two things we make. And what are those? There can only always be two things if you are going to complete combustion. Fantastic. Carbon dioxide and water. Okay, those are the only two things that you will make. Whenever you see combustion reaction, you can just literally blindly write down carbon dioxide and water. You cannot get anything else, regardless of what is on the left-hand side, okay? So carbon dioxide is CO2 and water is H2O. So that's done. That is basically my reaction. This is 2 marks. So there is 1 for writing it out and we need to balance it now. So let's have a go at doing this. So I have got 1 carbon here, fine. 4 hydrogens and 2 hydrogens here. Okay, and then I've got 3 oxygens on the left and I've got 3 oxygens on the right. So my hydrogens, they don't match up. So what I'm going to do is if I put 4 hydrogens here, that will give me 8. And then I've got 4 on this side, so I can put 2 here. And now that I've put 2 carbons, I'm going to put another 2 here. Okay, so that has then left me with 4 oxygens on this side and 8 oxygens and 8 oxygens on this side, and I've got 4 on this side. So basically if I put a 3 here, I can then get to 8. So does that work? So let's just count that up. So we've got 2 carbons, we've got 8 hydrogens and 8 hydrogens, and then we've got 8 oxygens, and then we've got 8 oxygens. So perfect. So that is correct. So this is basically just a lot of trial and error. But see, it's only worth 2 marks, but in the exam, this can actually take you like a good 5 minutes. So I would just suggest practicing a few of these, but it's very early on. So if you've got the basic idea, that is excellent. Okay, guys, well done. Thank you for putting up with me. So we're going to do a quiz now on alcohols. Okay, so let's just go to Kahoot. Okay, guys, so this is actually from Alkenes, but a lot of you have gotten this one mixed up. So remember that the alkenes will change color. So if it's alkanes, there will be no change. It will stay orange. And if it's an alkene, it will go from orange to colorless, okay? Okay, guys, so bromine water is orange, yeah? If you mix it with an alkene, the alkene reacts with the bromine and it becomes colorless. So it decolorizes. It doesn't turn orange. Bromine water is orange by itself. Sorry, I didn't tell you guys this. So alcohol, it's called an ol, but the OH group, we can actually call it hydroxyl as well. So well done. Fantastic, OH, well done. COH is carboxylic acid, and we will talk about that in another session. Okay, so this one has got one carbon, okay, so it will be meth, and it's got an OH group, so it will be methanol. Okay, and last question. Fabulous. Okay, everyone has got that one right. So as you can see, there are two carbons, so it will be eth, and there's an OH group, so it will be ethanol or ethanol.
Okay, that is amazing. Well done, guys. So you're all doing really well. We're just going to spend the last few 25 minutes or so just doing some exam questions and just really summarizing what we have talked about today. Okay, so let's have a look at these questions. And the aim is, don't worry about just trying to get the answer right, but just trying to understand and build your technique. Okay, so let's just highlight this question. So this question is about hydrocarbons. Great. Most of the hydrocarbons in crude oil are alkanes, yeah, saturated alkanes. Large alkane molecules can be cracked to produce more useful molecules. The equation shows the cracking of dodecane. Okay, we've never heard of this, that doesn't matter. So give two conditions used to crack large alkane molecules. So guys, put it in the chat. Do you remember what we said we need for cracking to take place? I know we've covered loads of reactions today. But it's really quite, it's just logic really. I mean, if you want to break something, what are you going to need? Are you going to make it cold, or do you want to make it hot? Do you need to speed something? Do you need there to be something to speed it up? So fantastic. So what do we need is we want to break this down. So we need a high temperature. Now, if you guys have said temperature, okay, that's not good enough. You're right, but you need to say high temperature, okay? Because temperature doesn't mean anything on its own. You need a high temperature and you need a catalyst, okay? So the high temperature gives it energy for it to take place, and the catalyst will speed up the rate of the reaction. Okay, so that's in 2 marks here. So let's have a look at the next one now. So the products hexene and ethene, okay, these ones here, these are alkenes. Complete the sentence. When alkenes react with bromine water, the color changes from orange to, okay, hopefully everyone can get this one. Fantastic, it's colorless, okay? So the color change is from orange to colorless. Okay, so bromine water is orange and it will become colorless only in the presence of an alkene. If you put an alkane, it's not going to work. So if you put this, nothing will happen. But these enes, they will react. Okay, great. So you can just see the mark scheme here. So it says high temperature, allow heating or hot, and catalyst, or you could say steam. Okay, so let's do another question. So crude oil is a fossil fuel. It's a finite resource. To make crude oil, it's useful to be separated into fractions. So crude oil is a, okay, what do you guys think? Okay, so there's a lot of mixed answers between mixture and with compound. So guys, the correct answer here is that crude oil is a mixture of different substances. Okay, and the reason it's not a compound is because it's not all joined together. Crude oil has got loads of different chains. Okay, but there is a mix of them. So some are long and some are short. They're not chemically combined to each other. That is a compound. So CO2 is a compound, but crude oil, okay, it's got methane in it. It's got decane. It's got butane. It's got loads of different substances within it, and these are not joined to each other. These are separate. Okay, and that is why we can use distillation to separate them. Otherwise, if it was a compound, we can't do that. So this is a mixture, okay, because they're not chemically combined. Okay, if you've got any questions on that, let me know. I can go back to this slide which told us that it was a mixture. Okay, let's have a look at the next one. The substances in crude oil have got different, what do you guys think? Fantastic. They have got different boiling points. Okay, that's nice and easy. And crude oil is separated by fractional what? Great. It's fractional distillation, isn't it? I think we have talked about that enough today. So it is distillation. Well done. The only other thing that you could get mixed up with is decomposition, but remember that thermal decomposition is totally different. That was when we use heat to break something down, and that is cracking as an example. Okay. Okay, so a few more nice questions. So crude oil is a mixture of many saturated hydrocarbons. They can be separated into fractions by the process of fractional distillation. State what is meant by hydrocarbon. Okay, so those of you that are paying attention will see that this is a 2-mark question actually. So for this one, you want to say 2 things. So just put your answers in the chat and we can go through them. And don't worry if you're not sure, just put it in anyway, because it's good to practice. So what is meant by a hydrocarbon? Okay, amazing. So all of you guys that have answered have got it correct. And the reason is because you've all said, so it's easy to say, yes, it contains hydrogen and carbon. Okay, that is what pretty much everyone will write down. But remember, we want to get full marks. So it contains hydrogen and carbon only. Okay, the second mark is for saying only. If as soon as you add in oxygen in here, it becomes an alcohol. Okay, so it's not a hydrocarbon anymore. So that is the correct answer there. Okay, great. So you get 1 mark for saying hydrogen and carbon and 1 for saying the word only. Okay, what is meant by saturated? So remember, we describe saturated as being that it's had enough or nothing else can be added on. And the reason is because it's got single bonds only. So you can say the proper definition is that it contains the maximum number of hydrogen atoms. Or you can say it's got single bonds only, okay? Either of these is fine. And yeah, they haven't given a mark for like no more hydrogen can be added. But if you write this, but I would just say this, I would just say single bonds only, okay? And what is a fraction? What does that mean? So what defines a fraction? Because we know that fractional distillation is when the oil gets separated into different fractions. But what exactly defines why it will split up in that way?
So basically, if something is a fraction, so guys, all of these, anything in a fraction, okay, they will be molecules of similar chain length. Okay, or they will have similar boiling points, yeah? So do you guys remember that tower that I showed you in the beginning when we had it here? I won't bother going back, but remember there were different bits in the tower and the liquids were coming out at different points and they were coming out at different fractions. Now, the reason that they were coming at different fractions is because they all have, at that point, they have the similar boiling points. There's similar chain length. So all the long ones will come out here and all the short ones will come out here. And that is the definition of a fraction. It's because they've got the similar boiling points, okay? So you guys all understand what a fraction is, but none of us actually said it in this way. So this is why we do exam questions, because even though you know what a fraction is, if you don't write it in the way that they want it, you won't get the mark, unfortunately. So great. Okay, so I've just put the answers here. So as you can see, carbon and hydrogen only, saturated means single bonds only, and fraction is molecules of similar chain length or similar boiling points or anything like that. Okay, so let's have a go at another question. Okay, so what does it say? So crude oil is a complex mixture of hydrocarbons, mainly alkanes. The number of carbon atoms ranges from 1 to over 100. How does the boiling point change as the number of carbon atoms in the molecule increases? What do you guys think? Okay, why don't you guys just pick one from this option, okay? How does the boiling point change? Do you think it will increase or decrease? Okay, fantastic, guys. So as the chain length increases, the boiling point increases. Remember, we did this in the morning, guys. So I started off by saying that if I had that one little methane molecule, okay, it's very easy for me to break this. If I then take a very long chain, okay, it's going to require much more energy for me to break this one down. So as the chain length increases, the boiling point will increase. Okay, it's not going to decrease. So you want to write this out very clearly. So the more carbon atoms, okay, the more the carbon atoms, comma, the higher the boiling point, okay? Okay, well done. Name the method used to separate petroleum into fractions. Okay, you guys should hopefully all be able to do this one. So they have added a bit of confusion by calling it petroleum, but essentially they are talking about the crude oil. Okay, so they called it petroleum, but basically it's got many different oils in here, many of the different hydrocarbons. So this is still fractional distillation. And even if you didn't know that, it's saying what do we use to separate into fractions. So there is really only one method that we use, and that is fractional distillation. Well done. Okay, so the simplest hydrocarbon is methane, CH4. Its structure can be represented as, draw the structure of ethane. Okay, so I think we might have seen this one. So this is very nice and easy. We've got two carbons.
Okay, and that is C2H6. It's from CnH2n plus 2. This is an alkane. Okay. Okay, let's have a go at this question. So complete the equation to bromine water can be used to show that hydrocarbon is ethene rather than ethane. Complete the equation to show the displayed formula of the product of the reaction between ethene and bromine. Okay, so guys, remember this is what we have seen. This is an addition reaction between an alkene and a halogen. Okay, and remember we said that this double bond is very reactive and the bromine wants to get involved, so it becomes a single bond. So it becomes single, and the bromines, they want to join up. Okay, so instead we will get bromine, bromine, and then these H's will stay on. And this is basically what I will form. That was dibromoethane, okay? So that is my displayed formula. So hopefully you guys will have got that one. So which is the correct statement about this test? Okay, what do you guys think? A, B, C, or D? Okay, fantastic, guys. So the product of the reaction is colorless, okay? So the color of ethene is not brown, is not a white precipitate, and this is not substitution. I've already said it's addition, so it can only be C, colorless, yeah? Okay, and just a few last questions. So the cracking of large molecules obtained from crude oil is one of the most important processes. Cracking involves thermal decomposition. The diagram below shows an apparatus. Apparatus, by the way, just means equipment that can be used to demonstrate cracking in the lab. The porous pot acts as a catalyst. Okay, so they have something here called a porous pot. What happens during thermal decomposition? Okay, tell me, guys. So guys, the answer is in the question. What does thermal mean? Thermal means heat, doesn't it? And what does decompose mean? Decompose means it is breaking down. Okay, so we are using heat to break down this substance. Okay, so what we can say is that the long chain alkane breaks down into a shorter chain alkane in the presence of heat. Okay, so you get 1 mark for saying that it's breaking down, and this is occurring because of the high temperature. Okay, and you can also say that you get a shorter chain alkane and you also get an alkene as well, but they're basically asking about thermal decomposition. So the mark here is for saying that it is heat. They're not asking you what is cracking, okay, because then if they ask you what's cracking, you need to say you make an alkene, yeah? Okay, what effect does the porous pot catalyst have on the reaction? So catalysts in general, they all that they are there for is they speed up a reaction without being used. We have many catalysts in biology and in chemistry. So this is a really easy question. And even if you don't know what porous pop means, or you have no idea what's going on in this experiment, okay, a catalyst will speed up the rate of the reaction. So even if you get an experiment which is really unfamiliar and you think, oh no, I've never seen this, I don't know what this is, use what you know, okay? We know that catalysts will always speed up the rate of the reaction. Well done. Okay, and then so complete the equation below for the cracking of the molecule C20H42. Okay, so they're telling you that they've cracked this to C12H26. So what's going to be left? So this is basically like a maths question, to be honest. So what will the other thing be that's left? So obviously remember, what's on the left has to balance what's on the right. We don't lose any molecules, nothing disappears. So I've got 20 carbons here, and I've only got 12 here. So I know that I must have 8, okay? There must be, because 12 plus 8 is 20. I can't have just lost a carbon, and there's not going to be a carbon magically appearing, okay? What's on the left will stay on the right. I've got 42 hydrogens here, but I've only got 26 here. Okay, so what that means is that you just do 42 minus 26, which is 16. So I must have 16 hydrogens, okay? And if you are lost about this, you will know that the alkenes have got the formula CnH2n. So if it's C8, it must be H16, okay? So that makes sense. This is an alkene, it's octene, and this is my alkane. Okay, and ethane is an alkane with the formula C2H6. Draw a ring around the correct answer to complete the sentence. Alkanes are hydrocarbons with the general formula. Okay, guys, nice and easy one to end off with. What do you guys think, A, B, or C? Okay, great. So the correct answer here would be C, CnH2n plus 2. Okay, and then last question. So diesel oil is obtained from crude oil. It can be used as a fuel. The diagram below represents a compound found in diesel oil. What is the formula of this compound? Okay, guys, so literally all we have to do is just count this one up. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, okay? So I know I've got C16. Now you can sit there counting this, okay, but we just said that this has got single bonds only. So it's CnH2n plus 2. So I know that this must be 16 times by 2, which is 32, plus 2, which will be C16H34, okay, and that is my alkane. Okay, guys, so that was the, I think we will stop there. All of these questions are in the packs. So what I want you guys to do is if you can do these questions for your homework and just try and go through what we've done, especially over your Christmas break.
But thank you guys. I know that was quite a lot today, so well done. You're all doing really well. And I hope you have a lovely Christmas break and a happy new year. This was our last session for 2020. So I will see you guys back in the new year in January. And if you've got any questions, as always, please feel free to drop us a message. Otherwise, take care and enjoy your Christmas break. Oh, and also if you guys can please fill in the feedback form if you get the chance, just so we can help make these sessions as useful as possible for you guys. Take care, bye.